Hello there and welcome to Life Beyond Seen, where curiosity drifts slowly like a current and science takes the scenic dive into places most of us never get to see. Tonight's journey is going to take us somewhere that feels almost impossible to imagine, a place so deep and so strange that even the word remote feels too casual. We're descending to the Hadopelagic zone, the very bottom of the ocean's trenches, a part of the planet that might as well be another world. Few creatures live there, even fewer humans have visited, and yet it exists beneath our feet, wrapping around the globe in silence. Before we begin, let me ask you something. Where are you listening from tonight? Are you close to the sea, maybe within reach of waves and salty breezes, or are you far inland where the thought of an ocean trench feels as distant as outer space? It's funny, isn't it? How some of us fall asleep to the sound of traffic or crickets, while right now, several kilometres beneath the Pacific Ocean, there are creatures drifting in total darkness, never knowing the sun even exists. If this gentle descent feels soothing, or if you enjoy these explorations into science at the edge of mystery, I'd be grateful if you gave this video a like, maybe subscribe to the channel, or even shared it with someone who might need a quiet way to end their day. It helps this little corner of calm reach others. And now, if you're settled, let's begin the long, slow dive, a journey downward into the deepest waters on Earth. The Hadopelagic zone starts around 6,000 metres below the surface and extends down to nearly 11,000 metres in the deepest trenches. To put that in perspective, if you took Mount Everest, the tallest mountain on land, and placed it upside down into the ocean, the peak would still not reach the bottom of the Mariana Trench. That's how deep we're talking. A place so far below the surface that no sunlight has ever reached it. Down there, the pressure is unimaginably intense, the cold is constant, and the darkness is absolute. And yet, life has found ways to survive. Not just survive, but adapt in ways so peculiar and unexpected that scientists are still trying to understand them. But before we get too far into the inhabitants, let's pause for a moment and think about this idea of depth. When we say 6,000 metres, 7,000, even 11, it becomes easy to treat those numbers like any other measurements. But the human mind isn't really designed to picture distances on that scale, especially vertical ones. We're used to walking across flat ground or climbing up a hill, not imagining a drop so long it could swallow entire mountain ranges. Even scuba divers, who go down perhaps 40 metres, 100 at most for recreation, are still closer to the surface than to anything that resembles the hadal depths. At 40 metres, light is still visible. At 100, you're dealing with serious risks but still within the reach of sunlight. By the time you get 1,000 metres down, the last trace of natural light is gone. Everything beyond that exists in what's called the midnight zone, and then, beyond the midnight zone lies the abyssal zone stretching down to about 6,000 metres. But deeper still, beyond that, lies the Hadopelagic. That's where we're heading tonight. Imagine sitting in a submarine as the light above you fades away, as the water pressure outside increases with every metre, and as the temperature drops to near freezing. At first, it's unsettling but still familiar. Then, after hours of descent, the sense of scale disappears entirely. The ocean above you becomes so thick and heavy, it's almost like a different substance altogether. If you could open the hatch, which of course you can't, the water would crush you instantly. At 11,000 metres, the pressure is more than 1,000 times greater than at the surface. To put that in relatable terms, it's like having 50 jumbo jets stacked on top of you. And yet, for the creatures who live there, this isn't crushing. This is simply normal. Their bodies aren't built like ours. Their flesh, bones and cells have been shaped by millions of years to endure a world where pressure doesn't feel like an enemy, but a condition of life itself. Even as we sit here thinking about it, there's a certain odd comfort in knowing that while we argue over schedules and rush to meetings, entire ecosystems are existing far below us without ever knowing our world above. It's humbling to realise that the planet has rooms we almost never visit, corridors we've barely mapped, and inhabitants who live in ways that challenge our very definition of what's possible. Scientists often compare the Hadopelagic zone to outer space, not just because of its inaccessibility, but because of the way it forces us to rethink what life can be. In fact, some believe that studying organisms from these depths could help us understand how life might exist on other planets or moons where conditions are equally extreme. But for now, let's stay here, drifting down slowly, with the creak of a submarine hull in our imagination, feeling the strange sensation of sinking past layers of ocean that very few eyes have ever seen. It's one thing to look at a map and trace the outlines of the Mariana Trench or the Tonga Trench, and another to imagine yourself suspended in the silence at the bottom. No surface glimmer, no moonlight refracted, no distant shoreline. Just cold water, crushing weight, and the faint flicker of organisms whose bodies glow with their own light. The first explorers who managed to reach these depths described an almost dreamlike silence, as if the ocean swallowed even the idea of sound. Of course, sound does travel in water, and in fact it travels faster than in air. But to the human ear, sealed inside a small vessel, it feels like an absence. Just the occasional groan of metal resisting pressure, the hum of machinery, maybe a faint crackle in the distance from shifting rocks or distant animal calls. Otherwise, it's a world without the noises we associate with life. No birds, no waves, no wind. Just stillness. It's strange to think about how much of the ocean we still haven't explored. Even today, in an age of satellites and advanced robotics, more than 80% of the seafloor remains unmapped. The hadal trenches are even less understood. Some have only been visited once or twice by human-made submersibles, others not at all. They sit there, kilometres below, their ecosystems unfolding whether we notice or not. In that sense, listening to this story is a little like shining a small flashlight into a vast dark cave. You only illuminate one tiny part, while everything else stretches into mystery. And maybe that's what makes the Hadopelagic zone so fascinating. It reminds us that the Earth is still wild, still largely unknown, still holding secrets even in an age where we carry more computing power in our pockets than the machines that first landed people on the moon. We often think of exploration as something belonging to the past, a time of ships setting out across unknown seas. But right now, at this very moment, there are frontiers beneath us that are less familiar than Mars. You might even say we know more about the surface of the moon than about the floor of our own ocean trenches. So here we are, preparing to explore, at least in thought, a part of the planet where few humans have ever set foot. And maybe that's what makes this such a perfect subject for a quiet evening reflection. The deep ocean doesn't rush. It doesn't care about deadlines or clocks. It simply exists, slowly, silently, eternally. As we imagine ourselves lowering into it, perhaps it helps us slow down too, letting go of the rush of surface life and sinking into the quiet of something far older, far steadier. When we talk about the Hadopelagic zone, it's tempting to treat it as a footnote, a distant afterthought in the long list of Earth's environments. But really it's more like the basement of the planet, that hidden level most people never enter, yet one that runs deep beneath everything else. Calling it a basement might sound a little casual, maybe even dismissive, but it fits in an odd way. Think of your own home or a place you visited that had a basement. It's below everything, rarely seen, often mysterious, sometimes cluttered with things you didn't know were still there. The Hadopelagic is like that, except instead of boxes and forgotten furniture, it holds alien landscapes and strange forms of life. The ocean has many levels. Scientists divide them in part by how far sunlight reaches. At the top there's the epipelagic zone, the sunlit layer where most fish we know live, where photosynthesis happens, where plankton float and whales rise to breathe. Below that lies the twilight zone, dim and hazy. Then comes the midnight zone, completely dark. Beneath that, the abyssal, stretching, vast and cold. And finally, At the very bottom, the hadal trenches. These trenches aren't broad, open plains. They're narrow, steep-sided cuts in the seafloor, formed by tectonic plates colliding, with one plate forced beneath another in what's called subduction. The deepest of them, the Mariana Trench in the Western Pacific, goes down nearly 11,000 metres. Others, like the Tonga Trench, the Kermadec and the Philippine, reach similar depths. Together they carve a jagged outline around the Pacific Rim, like scars on the skin of the planet. It's worth stopping for a moment to consider how enormous the ocean truly is. More than 70% of Earth's surface is covered by water, and the average depth of that water is about 3.5 kilometres. That's just the average. The hadal trenches nearly triple that distance. If you drained the oceans completely, the continents would look like tall, jagged islands rising out of vast empty chasms. The trenches would be the deepest scars, some stretching hundreds of kilometres long, yet so hidden underwater that most of us never even think about them. In a sense, these places are like secret rooms at the bottom of an already massive house. When people first began to explore the sea, they didn't even imagine such depths. Ancient sailors thought of the ocean as frightening, but they pictured it mostly in terms of surface storms, waves and monsters that might leap up from below. They had no way of imagining that miles beneath their ships lay landscapes as tall and dramatic as any mountain range. Even as recently as the 19th century, scientists argued about whether life could exist below a few hundred metres. The pressure was thought to be too great, the darkness too complete, the environment too barren. That idea, sometimes called the azoic hypothesis, suggested that the deep ocean was lifeless. But the deeper people probed with nets, dredges and eventually submersibles, the more evidence piled up that life not only existed but thrived. Still, it wasn't until the 20th century that we began to get the first real glimpses into the trenches. In 1960, the Trieste, a bathyscaphe piloted by Jacques Picard and Don Walsh, descended into the Challenger Deep, the deepest known point of the Mariana Trench. They made it all the way to nearly 11,000 metres. The descent took nearly 5 hours. The view, once they settled on the bottom, was limited by silt stirred up by their landing, but what they did see surprised them. A flatfish-like creature, possibly a sole or flounder, and small shrimp-like crustaceans. The hadal basement wasn't lifeless after all. It was just waiting for us to look. When you think about basements, you might picture dust, darkness, and forgotten things. The Hadopelagic zone shares some of that atmosphere, but on a scale far grander and stranger. Down there, the walls of trenches rise like cliffs, sometimes more than 100 kilometres apart, sometimes narrowing into steep valleys. The seafloor is uneven, littered with landslides of sediment, rocks carried down from above, and deposits that have accumulated over millions of years. In some areas, hydrothermal vents release mineral-rich fluids, creating oases of life in an otherwise barren setting. In others, the floor is covered in fine, silty mud that captures the remains of organisms drifting down from the upper ocean. It's easy to imagine the hadal trenches as silent and still, but in reality they are shaped by tectonic activity. Earthquakes, landslides, and volcanic eruptions happen there. Some of the strongest earthquakes ever recorded, like the one that struck off the coast of Japan in 2011, originate in these deep subduction zones. The seafloor is not static. It shifts, buckles, and grinds. To live in the Hadopelagic is not to float in eternal calm, but to survive in a landscape that occasionally shakes with the force of the planet itself. And yet, life is there. Amphipods, shrimp-like creatures, scavenge on whatever organic matter sinks to the bottom. Snailfish, pale and gelatinous, drift along, their bodies adapted to pressure that would crush most others. Microbes colonize rocks and sediments, living off chemical reactions with minerals instead of sunlight. These are not the crowded coral reefs or bustling kelp forests we picture when we think of marine life. Instead, it's a sparse but persistent community, spread thin across the trenches, each organism perfectly adapted to its niche. Calling it the ocean's basement doesn't just suggest hiddenness, it also suggests resilience. In your own basement, you might find things that have been sitting for decades, unchanged, surviving in a forgotten corner. That's what the hadal trenches are like. Some species may have remained relatively unchanged for millions of years, shaped slowly by the extremes of pressure and darkness, living in ways that are stable and ancient. Others may be specialized forms, adapted to conditions so narrow and specific they couldn't survive anywhere else. It's an ecosystem defined by endurance more than abundance. But basements are also places of mystery. You never really know what you'll find until you go down there. Every time researchers send a remotely operated vehicle or a lander into the trenches, they discover something new. A previously unknown species of snailfish. Amphipods with strange biochemistry that resist the toxic effects of pressure. Microbes that can digest substances toxic to most other forms of life. Even in recent years, plastic pollution has been found in amphipods from the Mariana Trench, a reminder that human influence reaches even the farthest corners of the planet. The basement may feel remote, but it is not untouched. For scientists, studying the Hadopelagic zone is not just about cataloguing strange organisms, it's also about understanding how life adapts to extremes. The pressures there are greater than what most laboratory equipment can simulate. Temperatures hover just above freezing. Food is scarce, arriving only in tiny flakes of organic matter drifting down from above, sometimes supplemented by a larger event like the fall of a whale carcass. And yet, organisms have evolved to endure it all. Their proteins are stable under immense pressure. Their membranes remain flexible. Some even have unique enzymes that allow them to function in ways that would break down in more normal conditions. The ocean's basement is also a record keeper. Sediments at the bottom of trenches capture materials from above and preserve them. By studying those sediments, scientists can learn about past climates, ocean chemistry, and even the history of life itself. It's like a filing cabinet that slowly collects layers of evidence year after year, century after century. Some of those layers go back tens of millions of years, holding clues about times when the Earth looked very different from today. It's humbling to think that while most of us go about our daily lives, these hidden basements are accumulating history beneath us. Every particle of marine snow that drifts down, every shell that sinks, every carcass that finds its way to the bottom becomes part of a story written in mud. And yet, the organisms living there are not just passive participants in this process. They interact with the sediments, recycle nutrients, and shape the chemistry of the environment. Even in the planet's darkest basement, life is not just surviving, it's influencing the world above. So when we call it the ocean's secret basement, we're not just talking about depth. We're talking about a place that holds the forgotten, the mysterious, the enduring, and the surprisingly vital. A place that seems far away, but is connected to the surface in ways we're only beginning to grasp. And as we continue our descent, the strangeness and wonder of what lives there will only become clearer. When you first hear that the Hadopelagic zone lies under 6,000 meters of water, the number feels almost abstract. It's just a figure on paper, a measurement like any other. But to understand what life faces down there, you have to translate that distance into pressure, because every meter of water pressing down adds weight, and by the time you've descended into the trenches, that weight has become something almost beyond imagination. At the surface of the ocean, we live under one atmosphere of pressure, the weight of the air above us. We don't notice it because our bodies are adapted to it, balanced inside and out. But descend 10 meters into the ocean, and the pressure doubles. At 100 meters, it's 10 times greater than what we feel up here in the air. By 6,000 meters, you're looking at 600 times atmospheric pressure. At the deepest point, nearly 11,000 meters, the weight pressing on every square inch is more than 1,000 times what you experience while sitting comfortably at sea level. To put it in a way that makes sense outside of numbers, imagine balancing an elephant on a postage stamp. That's the kind of pressure the organisms at the bottom endure constantly. Another way to picture it is to imagine the Eiffel Tower placed on your thumb, not once, but dozens of times over, and that weight distributed evenly across your skin. It's almost comical in how disproportionate it sounds, but for life in the Hadal trenches it's not exaggeration, it's reality. For us, that kind of pressure is instantly lethal. If a human body were exposed without protection, the gases in our tissues would be forced out, our lungs would collapse, and the delicate structures of our cells would break apart. Even the strongest submarines must be engineered with materials designed to withstand such stress. The Trieste, the first crewed vessel to reach Challenger Deep, had a pressure sphere with walls nearly 12 centimetres thick, made of specially cast steel. Even then, as it descended, the outer structures groaned and creaked under the stress. Later vehicles like James Cameron's Deep Sea Challenger or modern remotely operated landers use advanced composites, titanium, or thick glass spheres for cameras and sensors. Every descent is a battle against the crushing grip of water. And yet, fish live there. Amphipods scuttle across the bottom. Microbes grow in sediments. Their bodies don't collapse. Their cells don't burst. And they go about their lives as if nothing extraordinary were happening. The secret lies in how biology adapts. Pressure doesn't just squeeze from outside, it changes how molecules behave. Proteins, the molecular machines of life, normally fold into specific shapes to do their work. At high pressure, those shapes can unravel. Cell membranes, normally flexible and fluid, can become rigid. Enzymes that speed up chemical reactions can slow or fail entirely. Life in the trenches has found ways around this. Many organisms use special molecules called piezolites, compounds that stabilize proteins and keep them functional under pressure. Trimethylamine N oxide, or TMAO, is one such molecule. If you have ever noticed a particularly strong, fishy smell in seafood, that comes in part from TMAO breaking down. In deep-sea fish, levels of TMAO rise with depth, giving them the resilience they need. At the greatest depths, the concentration becomes so high that it may actually limit how deep vertebrates can go, which might explain why snailfish are found at around 8,000 metres, but not much deeper. Cell membranes adapt too. Instead of stiffening in the cold and under pressure, they contain more unsaturated fatty acids, which remain flexible, allowing cells to function. Bones, which would normally be brittle under such conditions, are reduced or absent in many species. Deep-sea fishes often have cartilaginous skeletons or gelatinous tissues that don't resist pressure but yield to it. By avoiding rigid structures, they avoid breaking. Some of the largest amphipods collected from trenches look almost ghostly, their bodies soft and translucent, like fragile balloons drifting in the dark, and yet they endure forces that would flatten steel. It's a reminder that what feels impossible to us is simply normal for them. To a snailfish, there's nothing unusual about living at depths where pressure could crush a submarine. To an amphipod scavenging on the floor of the Kermadec Trench, the crushing weight of water is just the background condition of life. Pressure isn't an obstacle, it's the environment itself. There's something humbling about realizing that adaptation doesn't always mean fighting against the environment. Sometimes it means yielding to it, finding ways to exist in harmony with forces that would seem hostile. Humans tend to engineer resistance. We build thicker walls, stronger alloys, reinforced systems to withstand stress. Hadal creatures take the opposite approach. They avoid rigidity, soften their bodies, alter their chemistry. They don't resist pressure. They dissolve into it. But pressure does more than shape biology. It also shapes geology. At these depths, the very seafloor is pressed and folded. Subduction zones push one plate beneath another, compacting sediments, creating earthquakes, and sometimes triggering tsunamis. The pressure from above adds to the immense forces from below, producing environments that are unstable, restless, and full of hidden energy. When a submarine lands on the trench floor, it doesn't just rest on solid ground. Often, it stirs up fine silt that's been compressed for ages, a cloud that drifts slowly because the water is so still. The idea of ground feels different down there, more like soft memory foam than hard rock. For the creatures that live there, pressure is inseparable from every other aspect of their existence. It influences how sound travels, how chemical reactions occur, how energy is stored and used. Even something as simple as gas bubbles, which in shallow waters form easily, are impossible down there. That means no air bladders for buoyancy. Fish in the trenches rely on different methods, like storing oils or reducing their bone density. Pressure strips away options and forces innovation. It's also worth considering how pressure interacts with human imagination. For most of history, people assumed the deep ocean was empty precisely because they couldn't imagine life withstanding such crushing force. The human mind often treats extremes as barriers: too hot, too cold, too dry, too deep. But life doesn't draw those lines as neatly. It finds a way, often by exploiting chemistry we hadn't thought of. The fact that amphipods digest plastics or microbes metabolize methane in these depths shows just how inventive biology can be when faced with what we'd call impossible conditions. When scientists bring deep-sea organisms to the surface, many don't survive. It isn't the lack of food or the change in temperature that kills them. It's the sudden release of pressure. Their cells rupture, their enzymes fail, their structures collapse. To truly understand them, researchers have had to build pressurized containers that keep samples at trench-level forces even as they're brought up for study. It's one of the biggest technical challenges of deep ocean biology, not just reaching the organisms, but keeping them alive long enough to learn from them. And yet, every success adds to the picture. Each new sample reveals adaptations we hadn't thought possible. Some amphipods, for example, have aluminum in their exoskeletons, likely scavenged from sediments. The metal seems to help them resist pressure-induced damage. It's the kind of solution no engineer would have dreamed up, yet evolution arrived at it through trial and error over countless generations. The more we learn, the clearer it becomes that pressure doesn't just challenge life, it sculpts it. Without the crushing weight of the ocean above, these creatures wouldn't look the way they do. Their strange bodies, their chemistry, even their behaviours are answers to a riddle written in water and gravity. As you picture the Hadopelagic zone, it helps to remember that pressure isn't a detail. It's the defining characteristic of the environment. Darkness can be found at shallower depths. Cold is present in much of the ocean. Scarcity of food is an issue across many ecosystems. But pressure at this scale is unique to the trenches. It is the signature of the hadal world, the constant presence that shapes every adaptation and limits how far life can descend. Thinking about this, it becomes easier to appreciate why so few species make it down there. The adaptations required aren't minor adjustments, they're complete redesigns of how bodies work. A coral reef fish dropped into the Mariana Trench would not simply struggle, it would disintegrate. But a snailfish, pale and gelatinous, feels no strain at all. It glides through pressure that to us is inconceivable. Its cells quietly supported by chemistry, tuned over millions of years. And maybe that's the real lesson of pressure. What seems impossible to us isn't impossible in itself. It's only impossible for us. Life, given enough time and variation, can solve puzzles we can barely understand. To live under 1,000 atmospheres of pressure, to thrive without collapsing, is just one more solution in nature's endless repertoire. If the crushing weight of water is one half of what defines the trenches, then the absence of light is the other. Down in the Hadopelagic zone, there is no sunrise, no shimmer from the moon, not even the faintest blue glow from the upper layers of the sea. It is a darkness that has lasted unbroken for millions of years, a darkness so complete it is difficult to describe to anyone who has never been without light. We are creatures of the surface, and even at night there is usually something to see. Streetlights, stars, the dim glow of the sky itself. Our eyes never experience true blackness unless we shut them, and even then, our brains often supply patterns or colours. In the hadal trenches, none of that exists. There is only the eternal dark. At first, this sounds like emptiness, as if nothing could happen in a place where sight is useless. But that's not true. The absence of light has not stopped life from flourishing in its own way. Instead, it has shaped it. In fact, darkness may be just as powerful an environmental force as pressure or cold. The creatures that live here don't rely on vision the way we do. Many are blind, their eyes reduced or absent altogether. Others have eyes but use them differently, tuned to catch the faint glow of bioluminescence rather than sunlight. Some create their own light, tiny flashes or slow pulses generated by chemical reactions inside their bodies. In a place without sunlight, light itself becomes a form of language. But let's slow down a little. Imagine yourself dropping steadily through the water column. Above, the surface fades, the colours vanish one by one. Reds disappear first, then oranges, then yellows. By 100 metres down, the warm end of the spectrum is gone, leaving only greens and blues. At 200 metres, even those begin to fade. By 1,000 metres, sunlight has vanished completely. Everything below that exists in what scientists call the aphotic zone, the lightless realm. It is here that the majority of the ocean lies, vast and unlit. The Hadopelagic zone is the deepest part of that aphotic world, the section where darkness is not just a condition, but a permanent law. For humans, the thought of endless dark is unsettling. We rely so heavily on sight that to take it away feels like losing not just a sense, but part of our identity. That's why deep-sea dives often describe a feeling of disorientation, even claustrophobia. Without reference points, without the horizon or a shaft of light, the mind struggles to find scale. Up and down lose meaning. You're simply floating in black. For the animals that live here, though, this is not a void. It's just home. Blindness in the trenches doesn't mean helplessness. Many species use other senses far more effectively. Amphipods, for example, detect chemicals drifting in the water, signals of food far away. Fish sense vibrations through lateral lines, tiny pressure-sensitive organs along their bodies. Microbes respond to gradients of chemicals or heat. In the absence of sight, life leans on other tools, and in a way that tells us something about ourselves too. We often treat vision as the dominant sense, but in truth, it's only one of many. Take it away, and other pathways open. In the trenches, darkness has forced life to specialise in ways we can barely imagine. The darkness also means there is no photosynthesis. Plants and algae that rely on sunlight to make energy cannot survive here. The base of the food web must come from above, drifting down as marine snow or from chemical reactions on the seafloor. That absence of light is not just a sensory condition, it's an ecological foundation. Without photosynthesis, the rules of life change. Instead of sunlight fueling a pyramid of producers and consumers, it is the fall of organic matter or the chemistry of vents that dictate survival. Still, the idea of total darkness is hard for us to accept. That's why stories of bioluminescence capture the imagination so strongly. The light generated by deep-sea organisms feels like rebellion against the abyss, tiny sparks against an endless black canvas. But in reality, it is simply adaptation. Some organisms use light to lure prey, others use it to confuse predators. Some communicate with pulses, like Morse code drifting in the water. A few, like certain jellyfish, emit light when threatened, creating a flash that distracts attackers. In the Hadopelagic trenches, where food is scarce and encounters are rare, those glimmers of light become essential. They are not decoration, they are survival. Think about what it means for light to become currency. On land, communication happens with sound or sight. In the trenches, light itself is transformed into a tool, a weapon, even a disguise. Some fish have lights that dangle like bait, mimicking the glow of smaller prey. Others have patterns along their bodies that break up their outlines, hiding them from predators in the dark. It's camouflage by illumination, a paradox that only makes sense in a place where true light doesn't exist. And yet, most of the time, the trenches remain dark. The occasional flash is just that. Occasional. For long stretches, hours, days, perhaps longer, the only illumination is the glow of microbes or the faint shimmer from an amphipod's body. It's strange to think of an entire world where daylight is not even a concept. If you were born in the Hadopelagic zone, you would have no word for sunrise, no sense of shadows, no idea of colour. Your world would be defined by touch, by chemistry, by vibration, and by pressure. To us that sounds alien. To the organisms there, it is normal. Scientists often compare this kind of environment to space. The darkness of the trenches is similar to the darkness between stars, vast and unyielding. But there is a difference. In space, darkness comes from emptiness. In the trenches, it comes from fullness, from the sheer thickness of water. The dark isn't an absence. It's the result of too much water between you and the sun, too much matter blocking the photons. In that sense, it's a crowded kind of darkness, heavy rather than empty. The absence of light also has psychological effects for humans who venture there. Submarine pilots have reported feeling as though they are suspended in ink, with no way to judge distance. Lights from their vehicles only illuminate a few meters ahead, and beyond that there is nothing. It's not like shining a flashlight across a room, it's like shining one into smoke. The beam fades quickly, swallowed by the black. Even the strongest lamps can't reveal more than a small circle. Beyond it, the unknown waits. For the animals, though, there is no fear. Generations upon generations have lived in this environment, shaping bodies and behaviours around the darkness. Some have no pigmentation at all, appearing pale or translucent. Others are red, a colour that disappears completely in deep water, effectively making them invisible. Predators that do have eyes are tuned to detect faint light, but even they see little compared to what we'd call vision. Their world is more about faint impressions, blurs of movement, the sudden glow of prey. What's fascinating is that even in complete darkness, patterns emerge. Organisms know when to feed, when to move, when to conserve energy. Many are influenced not by light cycles, but by the faint pull of tides, the gravitational rhythm of the moon and earth. Some even seem to detect the seasonal changes in food supply, linked to surface blooms thousands of meters above. In this way, the eternal darkness isn't entirely disconnected. It is part of a chain, responding to events far beyond its reach. It's easy to romanticize darkness as emptiness, but in truth, it is structure. The lack of light creates rules. It defines who can live there and how. It decides what strategies work and which fail. It has been shaping life in the trenches for millions of years, and without it, the ecosystems would look completely different. Eternal darkness is not just a backdrop, it is a player in the drama. And so, as we drift further into this world, the darkness continues to surround us, not as an end, but as a beginning, the condition from which everything else follows. The pressure crushes, the cold numbs, the scarcity limits, but it is the absence of light that defines what kind of life can even exist in the first place. In that sense, the trenches are not just deep. They are hidden in a way that goes beyond depth. They are hidden in a darkness that has never known a dawn. When people first imagine the deep sea, pressure and darkness usually come to mind. But once you sit with the idea of the Hadopelagic zone, there's another condition that deserves just as much attention. It's the cold. Not the kind of cold you feel stepping outside on a winter morning, when the air bites at your face and you know warmth is only a doorway away. This is the kind of cold that never ends, a chill that saturates everything, constant and unrelenting year after year, century after century. Down in the trenches, the temperature hovers just above freezing, usually between 1 and 4 degrees Celsius. It doesn't fluctuate with seasons, it doesn't warm during the day, and it never eases when the night comes because there is no night and day here. It's just the same steady chill pressing on everything. Cold in itself isn't unusual on Earth. The poles are cold, high mountains are cold, even some deserts at night are cold. But what makes the hadopelagic zone unique is the consistency. On the surface, weather shifts constantly. A warm day follows a storm or a sudden frost interrupts autumn. We're used to the climate around us being dynamic, sometimes even chaotic. Down in the trenches, stability is the rule. If you were to measure the temperature today and then again in 100 years, you'd likely find it almost identical. That sameness becomes part of the environment in a way that is difficult to picture from the surface. Imagine living in a room where the temperature never changed, not even by a single degree. For humans, that might feel reassuring at first, but eventually it would be unsettling. We're used to change, even small ones. For life in the hadopelagic zone, however, this constancy is the fabric of existence. The cold does more than create discomfort. It alters the chemistry of life itself. At low temperatures, chemical reactions slow down. Enzymes, the proteins that make reactions possible in living cells, work sluggishly. Membranes stiffen, molecules lose flexibility, and processes that on the surface take seconds may stretch into minutes. If pressure crushes, cold slows. Together they create an environment where metabolism must be rewritten. Organisms here have adapted in fascinating ways. Their enzymes are not the same as those in surface species. They are tuned to remain active at low temperatures, flexible enough to bend and twist when needed. Their cell membranes incorporate different fats, more unsaturated ones that resist stiffening, so that even at near freezing temperatures they remain fluid. Without those adjustments, their cells would lock up like frozen machinery. But with them, life continues, quietly, steadily, despite the cold. It's worth noting how different this is from how we usually treat cold. On the surface, cold is an enemy to fight. We wear clothes, build fires, heat our homes. In many parts of the world, survival itself depends on keeping the body warm. For deep-sea creatures, warmth is not even a concept. There is no alternative, no flame, no summer, no sunlight. Cold is simply normal. They don't fight it, they embody it. That doesn't mean the cold has no consequences. Growth tends to be slower in the deep. Lifespans, however, may be longer. Some amphipods or other invertebrates may live far longer than their shallow water relatives, in part because their metabolism is slower. Energy is used sparingly. Food is scarce, and so efficiency is essential. The cold helps enforce that efficiency. It's not just a challenge, it's a filter. Only organisms that can make peace with the slow pace of life survive. It's also striking to realise how the trenches connect to the larger ocean through cold. Deep waters are formed at the poles. When surface water cools, becomes dense and sinks. That water slowly circulates through the world's oceans, eventually reaching even the deepest trenches. In a way, the cold in the hadopelagic zone is a gift from the poles, a global current that carries chill into the planet's hidden basins. Every gulp of water taken by a snailfish or every swirl stirred by an amphipod has a history, perhaps beginning as melting ice in the Arctic or Antarctic centuries ago. The cold here is not local, it is planetary. Humans who have visited the trenches in submersibles describe a sense of being surrounded not just by water, but by stillness. Cold carries a psychological weight, even when you're shielded from it inside a pressurized cabin. The knowledge that everything outside is hovering just above freezing makes the environment feel inhospitable. It's not like being on a mountaintop where the air is cold but the sun still shines, and you can imagine stepping back inside a warm lodge. Here the cold is everywhere, inescapable, stretching thousands of meters in every direction. It doesn't simply exist outside your vessel, it is the entire world around you. For the organisms, though, that's precisely the point. Their very chemistry is designed for this cold. If you were to scoop one up and somehow warm it, even to what we'd call comfortable room temperature, it might not survive. Its proteins would unravel, its enzymes would fail, its membranes would collapse. Cold is not a hardship to them. It is a requirement. In this sense, the hadopelagic zone teaches us that comfort is relative. What seems deadly to us is home to others. What we treat as an extreme is to them the only possible environment. There's another aspect of cold that shapes the trenches. Sound travels differently in cooler water, often more efficiently. That means the calls of whales, the echoes of seismic activity, even the rumble of distant landslides can be carried vast distances. For the creatures of the hadal zone, vibrations may provide more information than sight ever could. In the still cold water, a tremor from kilometers away becomes a signal, a reminder that the surface world exists even if it's unreachable. The cold also interacts with pressure in ways that amplify the challenge. Low temperatures make gases less soluble. They alter the way molecules fold and interact. At surface conditions, we take for granted that oxygen and carbon dioxide behave predictably. At trench depths, with immense pressure and near freezing cold, those behaviours change. Organisms that live there have had to rewrite their physiology to cope with chemical laws that feel slightly bent compared to what we know. And then there's the simple fact of comfort. Imagine for a moment lowering your hand into near-freezing water and leaving it there. After a few minutes, it begins to ache. After a while longer, it goes numb. For a human, extended exposure to water, that cold is dangerous, potentially fatal. Now, imagine not minutes, not hours, but a lifetime in that environment. Every second of existence, every breath, every cell unfolding in a temperature most animals cannot tolerate for long. That is what it means to live in the Hadopelagic. It's tempting to see this as a grim picture, but in reality it's just different. The cold doesn't mean lifelessness. It means a different tempo, a slower rhythm. Metabolism is tuned down, movements are deliberate, growth is gradual. The stillness of the trenches is not empty, it's measured, and in that slowness, life finds a way to endure. Scientists studying trench ecosystems have noted that some species, particularly invertebrates, may accumulate less damage over time precisely because their metabolism is so slow. Fewer free radicals, fewer errors, slower aging. In a strange way, the cold may preserve them. The trenches are not just dark. They are ancient, not just in geology, but in the pace of biology itself. And while cold is often associated with sterility or stillness, here it creates a kind of quiet abundance. Not abundance in numbers, but in persistence. Microbes thrive in sediments, breaking down organic matter at rates adjusted to the chill. Amphipods wait patiently for food to arrive, sometimes fasting for long periods without harm. Snailfish glide unhurriedly, their gelatinous bodies perfectly suited to the pace of life here. Cold doesn't mean nothing happens. It means everything happens slowly, carefully, within limits. This constancy of cold has another implication. Unlike surface ecosystems where warming or cooling can disrupt life, the Hadopelagic zone changes little. That stability makes it a kind of archive. By studying organisms and sediments from the trenches, scientists can glimpse patterns unbroken for thousands of years. The cold preserves not only life but memory, holding on to signals from the past in ways more dynamic environments cannot. And yet, even here, human influence has reached. Plastics and pollutants have been found in amphipods from the Mariana Trench. Those chemicals, once released on the surface, eventually sink, carried by currents, locked into sediments, or ingested by scavengers. The cold doesn't prevent contamination. It just slows the breakdown. Pollution, once it reaches the trenches, may linger for centuries, held in a deep freeze the organisms can't escape. In that sense, the constancy of cold becomes a double-edged sword, a preserver not only of natural processes but of our mistakes. Still, the overall story is one of resilience. Life finds ways to adapt, whether through flexible membranes, altered enzymes, or slower metabolisms. The trenches remind us that cold is not inherently hostile. It's simply another condition, one that shapes existence as much as light shapes forests, or heat shapes deserts. For the creatures that drift and crawl in the Hadopelagic zone, Cold is not a problem to solve. It's the baseline of being. And so, as we imagine ourselves sitting in that eternal chill, it helps to let go of the idea that warmth is better. Down here, warmth would kill. Cold is not an intruder, it is the foundation. Everything else, pressure, darkness, scarcity, rests on that bed of icy constancy. It is the stage on which trench life plays out, a stage that has never shifted in living memory and likely never will. When you think of the ocean floor, it's easy to imagine a flat, sandy bottom stretching out endlessly like a desert beneath the water. That picture is reinforced by beach walks where the sand seems to go on forever, or by aquariums that show fish gliding over smooth gravel. But the reality of the seafloor, especially in the trenches, is nothing like that. It's rugged, uneven, and in many ways far stranger than any landscape you'd find on land. If you could drain the oceans and look at the Earth's skin uncovered, you'd see a world of ridges, valleys, cliffs and canyons so immense they would dwarf the Himalayas. The trenches of the Hadopelagic zone are not just low spots, they're alien terrains, landscapes sculpted by tectonic forces that keep reshaping them even now. The trenches exist because of subduction. One tectonic plate is pushed beneath another, forced down into the mantle, carrying sediments and water with it. This process creates narrow, elongated depressions in the ocean floor, some thousands of kilometres long, some more than 10 kilometres deep. They're not broad bowls like a lake basin. They're more like scars cut into the earth, steep-sided and sharp. If you were to stand at the edge of one, if such a thing were possible, you'd be looking down a slope so steep and so long it would take your breath away. The Mariana Trench, for instance, stretches about 2,500 kilometres in length and is more than 70 kilometres wide. At its deepest, the Challenger Deep, it plunges nearly 11,000 metres. That's like stacking Mount Everest and then adding another 2 kilometres on top of it, all inverted beneath the sea. The walls of these trenches are not smooth. They're jagged, fractured, layered with sediments that have slumped down over millennia. Landslides are common. Earthquakes can trigger cascades of mud and rock that tumble into the abyss. Some areas are riddled with faults, cracks that shift under pressure. Others are covered with thick mats of sediment, soft and unstable. A submersible landing on the trench floor often stirs up clouds of fine particles that hang in the water like smoke, taking hours to settle. It gives the impression of a ghostly shifting ground, more fluid than solid. The seafloor here is also punctuated by features that don't exist on land in the same way. Cold seeps and hydrothermal vents release chemicals into the water, creating localized environments full of life. At cold seeps, methane and hydrogen sulfide bubble up from beneath the sediments, feeding communities of microbes that in turn support clams, mussels, and other organisms. At hydrothermal vents, water heated by magma jets upward, rich in minerals, forming chimneys that look like spires from some other planet. Even in the deepest trenches, these features can exist, transforming patches of the seafloor into oases in an otherwise barren plain. What makes the trenches so alien is not just their scale, but their unfamiliarity. On land, we're used to gravity shaping landscapes we can see. Mountains rise, rivers cut valleys, erosion carves canyons. In the deep sea, the same processes occur, but hidden beneath water and altered by pressure and chemistry. A landslide in a trench doesn't just shift dirt. It reshapes an ecosystem that may have been stable for centuries. A volcanic eruption on the seafloor doesn't produce the fiery spectacle we imagine. Instead, molten rock oozes into water so cold it hardens instantly, creating strange pillow-like formations. The geology is active, but it looks and feels different from anything we know. Imagine walking across a plain of fine sediment, only it isn't solid. With every step you sink slightly, like moving across powdery snow. Around you, cliffs rise into darkness, their tops invisible. Occasional boulders jut out, dropped by landslides long ago. In the distance, a vent smokes mineral-rich water into the cold, forming chimneys taller than buildings. It feels like a dreamscape, a place where scale and form are exaggerated, a mixture of emptiness and sudden extremes. That's the alien terrain of the Hadopelagic. Even the chemistry of the ground is unusual. The sediments are often rich in organic material deposited from above. Marine snow, tiny flakes of organic debris, drifts down slowly, settling layer by layer. Over time it compacts into thick mats, recording the history of the ocean above. Sometimes you find traces of volcanic ash, evidence of eruptions from faraway islands. Sometimes there are microfossils, remnants of plankton that lived and died on the surface centuries earlier. The trench floor is not just a physical landscape, it's a geological archive, a place where time is written in mud. This alien quality is magnified by scale. On land, our reference points are small. 100 meters feels tall. A kilometer feels enormous. In the trenches, those numbers vanish into insignificance. A cliff could be 6 kilometers high. A canyon could stretch for thousands. When humans describe these places, they often reach for comparisons to space, not only because of the darkness and isolation, but because of the sheer vastness. Standing at the bottom of the Mariana Trench would be more like standing on another planet than standing anywhere else on Earth. And yet life has adapted to these strange landscapes. Amphipods crawl across slopes of sediment, scavenging on whatever falls. Snailfish drift close to the bottom, their bodies soft enough to withstand both pressure and the shifting terrain. Microbes colonize rocks, creating biofilms that turn mineral surfaces into miniature ecosystems. The geology and biology are intertwined. Where vents release minerals, microbial mats flourish. Where landslides deposit fresh material, scavengers gather. Where sediments pile up, worms and other invertebrates burrow and feed. The alien terrain isn't just a backdrop, it's part of the living system. Exploration of these terrains is still in its infancy. Most of what we know comes from remotely operated vehicles or autonomous landers that descend for hours before reaching the bottom. Their cameras send back ghostly images of slopes, plains, and vents. Often, the lights reveal only a small patch, a circle of illumination surrounded by blackness. Beyond it, the terrain stretches unseen. Each expedition reveals something new, a previously unknown species, an unexpected feature, a hint that we've only scratched the surface. For humans, part of the fascination comes from how inaccessible it all is. You can climb a mountain or walk into a canyon. You can't simply stroll into the Mariana Trench. Even the most advanced submersibles can only visit briefly, their time measured in hours. The terrain exists, immense and detailed, whether we see it or not. That sense of hidden vastness makes it feel alien, like a world that belongs to itself, indifferent to whether anyone observes it. It's also alien in the way it challenges our imagination. We're used to associating alienness with distance, with other planets, other galaxies. But here, beneath our oceans, lies a landscape just as strange, just as extreme, just as mysterious, and it's right under our feet. The fact that it remains largely unseen makes it more alien still. We know it exists. We can map its outlines with sonar, but the details, the textures, the daily life, the interactions of creatures with terrain remain unknown. What we do know suggests a place of constant interaction between the physical and the biological. Every rock, every slope, every vent becomes habitat. Every feature influences what can live there and how. The alien terrain is not empty. It's populated, shaped and reshaped by the lives that cling to it. Even microbes leave their mark, altering minerals, releasing chemicals, changing the chemistry of sediments. Life doesn't just exist in this terrain, it participates in it. And so, as we imagine ourselves continuing the descent, the picture of the trenches grows clearer. Not flat, not barren, but rugged, dynamic, and alive. The cold never lifts, The darkness never fades, and the pressure never relents. Yet in that environment, the Earth itself has sculpted landscapes as extraordinary as any in the solar system, terrains that remain alien precisely because we've seen so little of them. When you think about what it takes to survive in the trenches, the first instinct is to picture strength, maybe toughness or resistance, as if only the hardiest organisms could manage it. But that isn't the story the Hadopelagic zone tells us. Survival here is not about being the strongest in the way we usually think of it. It's about being the most adaptable, the most flexible, the most willing to bend rather than break. The art of survival in the deep doesn't look like armour or force. It looks like softness, like chemistry, like quiet persistence shaped by millions of years. Take the pressure. At 11,000 metres, the weight is crushing enough to collapse steel. No air bladders can exist there. No hollow spaces, no structures that resist too much. So what do the creatures do? They get rid of those spaces. Many hadal fish, like snailfish, have bodies with no swim bladder at all. Instead, they rely on oils or reduced bone density to control buoyancy. Their skeletons are thin, often cartilaginous, their muscles soft and gelatinous. They don't resist pressure, they yield to it. That softness, which would look fragile on the surface, is precisely what allows them to endure. Then there's chemistry. Proteins normally unravel under high pressure, losing their shape and function. The trench solution is piezolites, tiny molecules like tremethylamine N-oxide, or TMAO, that stabilize proteins and keep them folded correctly. The deeper you go, the more of these molecules you find in fish tissue. It's not an accident. It's a gradient of survival, a slow adjustment as depth increases, ensuring that the machinery of life keeps running even when the environment wants to shut it down. Adaptation is everywhere in their membranes too. Cold water tends to stiffen cell walls, but deep-sea organisms alter the composition of their lipids, adding unsaturated fatty acids that stay flexible even at near-freezing temperatures. Without that, their cells would be locked solid, unable to exchange nutrients or signals. With it, they remain supple, their internal processes flowing despite the cold. And then there are the scavengers. Food in the trenches is rare, so any survival strategy has to account for scarcity. Amphipods, for example, can gorge themselves when a large meal arrives, storing energy for weeks or even months. Some species have digestive systems that can handle almost anything organic, from marine snow to whale carcasses. Their adaptability is in their diets. They don't specialise in one food source because they can't afford to. The art of survival is being ready to eat whatever falls whenever it does. Other creatures shrink themselves. In an environment where energy is scarce, being small has advantages. Some trench organisms are miniature versions of relatives found in shallower waters, needing less food to survive. At the same time, others go the opposite direction. Gigantism shows up in amphipods and isopods, with some species growing far larger than their surface cousins. The reasons aren't fully understood, but possibilities include slower metabolism, allowing resources to accumulate, or pressure favouring certain body structures. Whatever the mechanism, both strategies, going tiny or going giant, work. Both are survival in action. Bioluminescence is another adaptation that feels almost like magic to us, but is routine in the deep. Organisms produce their own light using chemical reactions. Some use it to lure prey, dangling a glowing lure in the darkness. Others use it defensively, flashing to confuse predators or releasing glowing clouds to distract them. Some even use it to communicate, signaling to potential mates or rivals. In a world without sunlight, the ability to make light becomes a survival tool as essential as speed or strength. Microbes play their part as well. In sediments where sunlight never penetrates, they rely on chemosynthesis instead of photosynthesis, deriving energy from chemical reactions with methane, hydrogen sulfide, or other compounds leaking from the earth. These microbial mats form the foundation of trench ecosystems, supporting larger organisms like clams, mussels, and tube worms. Their adaptation is chemical creativity, turning what looks like an inhospitable landscape into a living one. Even reproduction is shaped by the demands of the trenches. Many deep-sea species produce fewer offspring than their shallow water relatives, but they invest more in each one, giving them larger yolks or better starting chances. In an environment where encounters are rare and resources limited, it's better to bet big on fewer chances than to scatter millions of larvae and hope for the best. That survival strategy written in the language of scarcity. And then there's longevity. Some trench species may live far longer than we expect precisely because of the slow pace of life. Metabolism is tuned down, growth is gradual, energy is conserved. Where surface species burn quickly and die young, hadal organisms extend their lives over decades, perhaps centuries. Their art of survival is patience, existing in a rhythm so slow we can barely grasp it. When humans first began studying these organisms, the adaptation seemed almost impossible. Fish without skeletons, enzymes that shouldn't work, creatures glowing in the dark. But over time it became clear that these weren't oddities, they were solutions. Each adaptation is an answer to a problem posed by the environment: pressure, cold, darkness, scarcity. Taken together, they form a picture of survival that feels alien only because it is unfamiliar to us. For the organisms, it's ordinary. It's simply life as they know it. It's worth pausing to notice the pattern here. Adaptation in the trenches is not about overcoming the environment, it's about aligning with it. Soft bodies yield to pressure. Flexible membranes yield to cold. Bioluminescence turns darkness into communication. Scarcity becomes patience. Every strategy is about fitting into the conditions rather than resisting them. It's survival through acceptance, a lesson as philosophical as it is biological. We tend to think of harsh environments as empty or hostile, but the Hadopelagic zone shows otherwise. Life doesn't vanish, it transforms. It finds ways to fold itself into the cracks, to rewrite its rules, to make the impossible ordinary. That's why every expedition into the trenches seems to reveal something new. Some species we didn't know existed, some adaptation we hadn't imagined. The basement of the ocean isn't barren, it's just different. And if there's an art to survival, it lies in that difference. Life doesn't argue with the deep. It doesn't resist the crushing weight or rail against the darkness. It bends, shifts, transforms, until the conditions that would kill us become the very framework of existence. Pressure becomes background. Cold becomes comfort. Darkness becomes communication. Scarcity becomes patience. It's not brute force survival, it's elegance, it's art. In the trenches, where sunlight has never reached, the idea of light takes on a completely different meaning. Up here at the surface, we take brightness for granted. The sun rises, floods the world with colour, and then the moon and stars take over at night. Even in cities where the stars are drowned out, there are street lamps and signs, headlights and screens. We're surrounded by light so constantly that true darkness feels rare and almost unnatural. But in the Hadopelagic zone, darkness is the permanent law, which is why the ability of organisms to make their own light feels so astonishing. Bioluminescence is not a novelty here. It's a survival tool, a form of communication, even a weapon. It's the language of whispers written in sparks and glows across an endless black canvas. At its simplest, bioluminescence is chemistry. Organisms produce light through a reaction between a molecule called luciferin and an enzyme called luciferase. Mix the two in the presence of oxygen, and photons are released. Some organisms generate their own luciferin. Others acquire it from prey or symbiotic bacteria. The result, though, is the same, a glow that cuts through the dark. It isn't heat-based like fire, it's cold light, efficient and subtle, visible without wasting precious energy on warmth. In an environment where resources are scarce, that efficiency is crucial. To us, a glowing organism feels magical, almost supernatural. But for the creatures of the deep, it's routine. Many species are bioluminescent, from tiny plankton drifting through the water to large fish lurking near the trench walls. Each uses the glow differently. Some release sudden flashes to startle predators. Others produce steady glows to lure prey closer. A few use patterns and rhythms, pulses and blinks, like a coded message drifting through the water. One of the most famous examples is the anglerfish. With its dangling lure, a glowing tip sways in the darkness, mimicking smaller prey. Curious creatures swim closer only to find themselves within reach of jaws waiting in the black. It's a trick, a deception written in light. Other species take the opposite approach. Some squid, for instance, produce bioluminescent ink. Instead of hiding in shadows, they hide in brilliance, releasing a glowing cloud that confuses predators long enough to escape. It's defense through spectacle. In the Hadopelagic trenches, where encounters between organisms are rare, bioluminescence becomes even more important. Imagine drifting in the dark, unable to see beyond a few centimetres, with food scarce and potential mates scattered across vast distances. A glow becomes more than a beacon. It becomes the only way to make contact. A tiny pulse of light might signal readiness to reproduce. A flash might warn rivals away. For species living at depths of 8,000 or 9,000 metres, where population densities are incredibly low, those signals can mean the difference between survival and extinction. There's a subtlety to this communication that makes the phrase whispers feel accurate. Unlike surface organisms that broadcast signals widely, bright feathers, loud songs, bioluminescence is often minimal, just enough for the intended recipient. It's not a shout across a crowd. It's a whisper in the dark, a signal carefully measured to be visible, but not too visible, because every glow carries risk. Light that attracts a mate might also attract a predator. A flash that warns off a rival might also betray your position. So the glow is used carefully, cautiously, often fleetingly. Scientists studying bioluminescence in the deep have noted how diverse it is. No two species use it in exactly the same way. Some produce blue light, the wavelength that travels farthest through water. Others produce green or even red, rarer in the deep, but sometimes more effective for specific purposes. Some lights are steady, others flicker. Some are localized, confined to organs near the head or tail. Others are spread across the body in patterns. It's like a hidden Morse code written in biology, 1,000 dialects of light spoken across the trenches. To human eyes, seeing it firsthand can be disorienting. Pilots of deep-sea submersibles have described drifting in complete blackness, only to suddenly witness flashes all around, like stars winking into existence. Some describe it as sitting inside a planetarium where the constellations rearrange themselves at random. Others say it feels like snowfall, only with sparks instead of flakes. In that moment, the darkness of the trenches doesn't feel empty. It feels alive. But for the creatures producing the light, it's not beauty they're after. It's survival. Consider a predator like a dragonfish, with long needle-like teeth and a body that glows faintly along its sides. The glow isn't random. It helps break up the fish's outline, making it harder for prey to spot. It's camouflaged by illumination, blending into the faint glimmers of the water itself. Prey swimming nearby sees nothing unusual until it's too late. Here, light is not just visibility, it's disguise. There are also organisms that weaponize light in unexpected ways. Some copepods release glowing chemicals into the water when threatened, essentially painting their attacker with a bright target. Predators, now glowing themselves, become vulnerable to being eaten by something larger. It's a biological trick turning the tables by making the hunter visible. The message is clear: attack me, and you risk drawing attention to yourself. This balance between attraction and risk means bioluminescence is often incredibly precise. Some species can control the timing of their flashes down to fractions of a second. Others can dim or brighten at will, adjusting the glow depending on the situation. It isn't a blunt instrument. It's a finely tuned survival strategy, honed over millions of years. Even bacteria play a role in these whispers. Some fish carry symbiotic bacteria in specialized light organs, providing them with a steady glow. In return, the bacteria get nutrients and a safe place to live. It's a partnership where light itself is the shared resource. That collaboration shows how deep adaptation goes, not just individual survival, but cooperative survival written in chemistry and photons. What makes all of this even more remarkable is how little energy is required. On the surface, light often comes at a high cost. Plants must capture sunlight. Fire burns fuel. Electricity requires infrastructure. In the trenches, organisms produce light using tiny amounts of energy, efficient enough to make it sustainable in a food-scarce environment. Bioluminescence is not wasteful. It's economical, every photon serving a purpose. It's easy to see why humans are fascinated by it. We've woven glowing creatures into myths and stories for centuries. Fireflies, glowing fungi, luminous plankton near the shore. But the scale of bioluminescence in the ocean, especially in the trenches, is far beyond anything on land. Some scientists estimate that more than 3/4 of deep-sea organisms use bioluminescence in some form. It's not rare, it's the rule. The Hadopelagic zone isn't just dark, it's full of quiet sparks, whispers of light drifting endlessly through the black. This perspective reframes what it means to think of the trenches as alien. We call them alien because they are unfamiliar, extreme, and hidden. But in truth, they are filled with signals, with communication, with interaction. They're not silent voids, they're whispering constantly, just in a language of light instead of sound. To us, it feels magical. To them, it's simply how life works. And as submersibles descend into these regions, carrying cameras and lights, we're often struck by how fragile it all looks. A single amphipod glowing faintly, a snailfish drifting with a shimmer along its fins, a sudden burst of plankton lighting up when disturbed. It feels like being allowed into a secret conversation, one not meant for us. We're intruders holding floodlights into a world that communicates in sparks, and yet, even so, we catch glimpses. The deeper you look, the more it becomes clear that bioluminescence isn't a side effect. It's central. In the absence of sunlight, it has become the stand-in, the substitute, the force that allows life to find each other, to feed, to mate, to survive. Without it, the trenches would be not only dark but silent in the truest sense. With it, they're alive with whispers. When you think about the creatures that live in the trenches, the first images that often come to mind are of enormous monsters. We've all seen illustrations of giant squids wrapping their arms around submarines, or enormous amphipods as big as dinner plates scuttling across the abyssal floor. There's truth in those images. Gigantism is common in the deep sea. Many organisms grow far larger than their shallow water relatives, but just as striking is the opposite trend. Some trench inhabitants are incredibly small, miniature versions of their cousins elsewhere. It's a paradox that seems contradictory at first glance. How can the same environment produce both giants and dwarfs? To understand it, you have to think about the conditions of the Hadopelagic zone. Food is scarce, pressure is immense, temperature is consistently cold. In such an environment, size becomes a strategy, but not one with a single correct answer. Sometimes bigger is better, sometimes smaller is. Evolution in the trenches has followed both paths depending on what offers the best chance of survival. Consider amphipods. In shallow waters, these shrimp-like crustaceans are usually only a centimetre or two long. In the trenches, some species grow up to 30 centimetres. That's 30 times bigger than their surface relatives. Why would an organism grow so large in a place where food is rare? One possibility is efficiency. Larger bodies can store more energy, allowing them to survive long periods without eating. A big amphipod can gorge itself when food does arrive, perhaps a whale carcass or a large piece of debris, and then live off that stored energy for weeks or months. Size becomes a way to smooth out the unpredictability of meals. Another factor may be pressure. Larger body sizes in some species might be structurally favourable under high pressure, giving stability in ways small, delicate forms could not. There's also the question of metabolism. Cold water slows metabolism, which means organisms don't burn energy as quickly. That slower pace can support larger bodies, because they don't require as much food per unit of mass as they would in warmer, faster-living environments. At the same time, many trench organisms go in the opposite direction. Snailfish, some of the deepest living vertebrates, are small, often no longer than 30 centimetres. Their bones are thin, their bodies gelatinous. They don't waste energy growing massive. Instead, they minimise conserving resources by keeping their form simple and light. In an environment where every calorie counts, being small can be the more efficient choice. Less energy to grow, less energy to maintain, less energy to reproduce. Survival through reduction rather than expansion. This is the paradox of size in the deep. Two strategies, both valid, both successful. Be large enough to store energy and endure long gaps between meals, or be small enough to need little energy in the first place. Both paths are extremes, and both reflect the pressures of the environment in different ways. There are other examples. Deep-sea isopods, close relatives of pill bugs, can reach the size of a loaf of bread. Meanwhile, some trench-dwelling microbes are tiny beyond measure, surviving in sediments with minimal resources. Giant squids lurk in the mid-waters above trenches, stretching more than 10 metres long, while tiny transparent crustaceans drift nearby, almost invisible to the naked eye. The deep doesn't favour one direction. It pushes organisms to extremes. What's interesting is that gigantism in the deep sea is not unique to the trenches. It appears at abyssal depths as well, but it becomes especially dramatic in the hadal zone. The combination of cold, pressure and scarcity amplifies the extremes. Scientists call this pattern deep-sea gigantism, and it has been observed in amphipods, isopods, squids, jellyfish, and more. The exact reasons remain debated, but the factors of slow metabolism, pressure adaptation, and energy storage all seem to play roles. On the other hand, miniaturization is also consistent with deep-sea conditions. It shows up in fish, invertebrates, and even some larger groups that produce tiny, simplified offspring. One theory suggests that small body size helps reduce predation risks. Another suggests that being small allows organisms to occupy narrow niches, using resources too limited for larger species. In the Hadopelagic, every niche matters, and smallness becomes a way to fit into cracks left by others. From a human perspective, size is often linked with dominance. We think of the biggest animals, whales, elephants, dinosaurs, as the rulers of their environments. But the trenches remind us that survival doesn't follow that logic. Here, giants and miniatures live side by side, each successful in their own way. A 30-centimetre amphipod and a 3-centimetre snailfish can both thrive, each with adaptations perfectly suited to their roles. Size is not about hierarchy, it's about strategy. The paradox also shapes how humans perceive the deep. Stories of giant squids fueled sailors' imaginations for centuries, turning them into myths of sea monsters. The discovery of actual large squid confirmed that some of those myths had a basis in reality. At the same time, the tiniest trench dwellers are just as alien, invisible to the eye but just as adapted. Both ends of the scale feel strange to us because they push against what we expect. We live in a world where most animals we encounter fall into a moderate size range. The trenches break that pattern, stretching it in both directions. There's also a lesson here about energy and time. Bigger organisms tend to live longer, slower lives in the trenches. Smaller ones often reproduce more quickly, taking advantage of brief opportunities. One strategy favours endurance, the other agility. Both are forms of survival, tuned to the conditions of an environment where meals are rare and encounters unpredictable. For researchers, this paradox poses challenges. Large deep-sea animals are difficult to capture and study because they often don't survive the trip to the surface. Their bodies collapse under the sudden release of pressure, their tissues breaking apart. Small ones, meanwhile, can be nearly invisible, slipping through nets or hiding in sediments. That means much of what we know is pieced together from brief glimpses, remote video, or preserved remains. Every expedition brings surprises. A giant amphipod collected from one trench, a tiny snailfish caught in another. Each discovery adds to the picture of extremes. And perhaps that's what makes the paradox so compelling. It tells us that survival in the Hadopelagic zone doesn't have one solution. There isn't a single blueprint for how to endure darkness, cold, and crushing pressure. Instead, there are multiple answers, sometimes opposite ones, each working because evolution has tested them across millions of years. Giant and tiny, both strategies whisper the same truth: adapt or vanish. So as we picture the alien terrain of the trenches, dotted with scavengers, microbes, fish, and strange crustaceans, we have to let go of our surface logic. Down here, size doesn't mean power. It doesn't mean weakness either. It means adaptation. Sometimes that adaptation leads to giants that seem almost absurd in their bulk. Sometimes it leads to miniatures that seem impossibly delicate. Both are valid. Both are alive. Both are part of the story of survival in the deep. When scientists first began exploring the Hadopelagic zone, many assumed no vertebrate could survive there. The pressure was simply too much, the environment too harsh, the conditions too extreme. Invertebrates like amphipods or sea cucumbers perhaps, microbes certainly. But fish? The idea seemed unlikely. Then came the discovery of the snailfish. Pale, soft-bodied, delicate-looking, yet thriving at depths greater than any other known vertebrate. It was as if a ghost had been found gliding through the trenches, a fish so improbable that its very existence rewrote what we thought was possible. Snailfish don't look like survivors, at least not by the standards of surface life. Their bodies are gelatinous, almost translucent, with thin bones and a lack of scales. Their skeletons are lightly calcified, their muscles soft, their appearance more like a drifting wisp than a solid animal. If you scooped one up and placed it in your hands, it would seem fragile, insubstantial, as if it might dissolve with a touch. Yet in the crushing pressure of 8, 9, even 10 kilometers beneath the sea, that softness is exactly what allows it to endure. Instead of resisting pressure, snailfish yield to it. They have no air-filled swim bladder, the organ most fish use for buoyancy, because any gas-filled space would collapse under hadal pressures. Instead, their buoyancy is controlled by gelatinous tissues, water-rich and compressible. Their bones, reduced and pliable, don't snap. Their flesh, soft and flexible, doesn't shatter. What looks weak is, in this environment, the ultimate strength. These adaptations make snailfish the champions of depth. The current record holder, a species found in the Mariana Trench, was filmed at nearly 8,200 meters, swimming with ease in conditions that would crush nearly every other vertebrate. Others have been collected from the Kermadec and Japan trenches, each discovery surprising scientists with just how deep fish can go. Beyond a certain depth, around 8,500 to 8,700 meters, theory suggests vertebrate life cannot exist, and yet snailfish push right up to that limit, as if tracing the very boundary of possibility. Their chemistry provides clues as to how. Snailfish have exceptionally high concentrations of trimethylamine N oxide, or TMAO, the same compound found in other deep-sea species to stabilize proteins against pressure. In snailfish, the levels are so elevated that they likely mark the upper limit for vertebrate survival. Beyond those depths, proteins may simply stop functioning, no matter how much TMAO is present. It's a chemical ceiling, and the snailfish live right below it. They are quite literally ghosts at the edge of existence. Watching them in submersible footage is uncanny. They drift with slow, unhurried movements, pale bodies blending into the silty seafloor. They don't look predatory in the way sharks or tuna do. They don't rush or strike with speed. Instead, they hover, then dart gently at small prey, usually amphipods. Their mouths open, their jaws snap, and the meal is gone. It's efficient, subtle, almost quiet hunting, perfectly suited to an environment where energy conservation is everything. And yet, despite their delicate appearance, they dominate their niche. In some trenches, snailfish are the top predators. Amphipods are abundant, and snailfish feed on them readily. They may look insubstantial, but they sit at the top of the hadal food chain, ghostly rulers of a silent world. Their abundance in some regions suggests they are not rare oddities, but central players in trench ecosystems. The discovery of snailfish has forced scientists to rethink limits. For decades, textbooks repeated the assumption that vertebrates couldn't survive past 6,000 meters. Pressure would break down proteins, distort membranes, collapse bodies. Then snailfish were found at 7,000, then 7,500, then past 8,000. Each new record nudged the boundary further down. It's a reminder that nature rarely conforms to our expectations. The Hadopelagic zone is full of surprises, and the snailfish embodies that spirit. There's something almost poetic about their ghostly nature. They have no bright colours, no bold markings, no flashy adaptations that stand out. They're pale, translucent, nearly invisible in their environment. They whisper through the darkness rather than announce themselves, and yet, that quiet presence has allowed them to thrive in one of the harshest habitats on Earth. It's survival through understatement, through softness, through blending in rather than standing out. The more scientists study them, the more questions arise. How do they find mates in such vast, sparse environments? How do their larvae survive, given that reproduction at such depths would be difficult? Some evidence suggests their eggs may drift upward, hatching in slightly shallower waters before the young descend. If true, that would mean snailfish span not just one environment but several, connecting trenches with the midwaters above. It would also explain how they maintain populations across such isolated habitats, using the water column as a highway for dispersal. Snailfish also challenge our perception of what predators should look like. We associate predators with strength, speed, sharpness. The snailfish lacks those traits in the obvious sense. Its teeth are small, its body fragile, its movement slow. But in the trenches, those traits aren't weaknesses, they're advantages. A body that doesn't waste energy on speed. A form that bends instead of breaks. A strategy built on patience and subtlety. That's what dominance looks like in the hadal world. For researchers, capturing snailfish has been both thrilling and heartbreaking. Thrilling, because every specimen confirms their ability to thrive where no other fish can. Heartbreaking, because most don't survive the journey to the surface. The sudden release of pressure is catastrophic. Their bodies rupture, their tissues collapse. Even when scientists design pressurized recovery containers, survival is rare. Much of what we know comes from fleeting glimpses on camera or from lifeless specimens collected by traps. The ghost of the trenches resists being brought into our world, vanishing when removed from its own. That elusiveness adds to their mystique. They exist, they thrive, but only where we can barely reach them. For the most part, they remain unseen, gliding through a darkness that belongs to them. Even our best technology gives us only fragments, a few minutes of footage here, a specimen there. Enough to prove they exist, not enough to fully understand them. It's as if the trenches keep their secrets close, revealing them only sparingly. And perhaps that's fitting. The snailfish doesn't need us to notice it. It doesn't need recognition or drama. It simply exists at the edge of possibility, soft and pale, a ghost swimming in silence. Its very presence is a quiet reminder that life is not confined by our expectations. Even in the deepest, darkest, coldest places, life finds a way. Sometimes that way is fierce and armoured, sometimes it's soft and ghostly. Both work, both endure. So when we think about the art of survival in the Hadopelagic zone, the snailfish is the perfect emblem. A creature that looks fragile but is in fact perfectly designed for the pressures of its world. A ghost that thrives where we thought no vertebrate could. Proof that in the darkest trenches of Earth, life not only survives but flourishes in forms we never imagined. If the snailfish is the ghostly ruler of the trenches, then the crustaceans are its tireless workers, the scavengers, foragers, and recyclers that keep the hadopelagic ecosystem alive. In many ways, they are the backbone of the trenches, even if their bodies are often small and soft. When a piece of organic matter falls from above, whether it's a drifting flake of marine snow or an entire whale carcass, it is usually the crustaceans who arrive first, breaking it down, feeding on it, and in the process making energy available to everything else. Without them, the trenches would not only be darker and colder, they would be silent in a more profound way, a place where life stalled instead of flowing. Amphipods are perhaps the most iconic of these crustaceans. In shallow waters, they are tiny, shrimp-like animals no bigger than your fingernail. But in the trenches, some grow to 30 centimetres or more, giants compared to their surface relatives. They look almost ghostly, with pale, translucent bodies that reveal their internal organs. Their adaptations are as fascinating as they are unsettling. Their exoskeletons, for example, are reinforced with aluminum, a metal they scavenge from sediments. How they do it is still being studied, but the aluminum seems to form a gel-like coating that may protect them from the crushing pressure and from dissolving in the slightly acidic waters of the deep. It's the kind of solution no engineer would have dreamed up. Yet evolution has perfected it over countless generations. Their diet is equally remarkable. Amphipods are opportunistic feeders. They eat anything organic they can find, from decaying fish to the soft tissues of whales, even plastics that have sunk from human activity above. They are not picky. In an environment where food is rare, specialization is a luxury. Their digestive systems are capable of extracting nutrients from a wide variety of materials, and their ability to gorge themselves when food is available allows them to endure long periods of scarcity. Some specimens pulled from trenches have stomachs so distended with food that their bodies appear bloated, evidence of a feast that will sustain them through weeks or months of famine. But amphipods are not the only crustaceans in the hadal realm. Isopods also make their presence known, though less dramatically than their amphipod cousins. These are relatives of the pill bugs you find in gardens, but on the seafloor they take on new proportions. Some deep-sea isopods grow to the size of a football, their bodies armoured and segmented with legs adapted for crawling across sediments. They move slowly, deliberately, scavenging on whatever they encounter. Like amphipods, they are resilient generalists, able to digest a wide range of organic material. Their size, their patience, and their tough exoskeletons make them well suited to the slow pace of life in the trenches. Crustaceans occupy every level of the hadal food web. They are prey for snailfish and other predators, but they are also predators in their own right, attacking weakened animals or stripping flesh from carcasses with astonishing efficiency. They break down what would otherwise be wasted, recycling nutrients in an ecosystem where nothing can go to waste. In this way, they are both humble and essential, the unsung recyclers of the abyss. The diversity among them is striking. Some are almost transparent, blending into the dark water. Others are tinted red, a colour that disappears completely in the deep ocean, rendering them invisible. Their bodies range from fragile and balloon-like to dense and armoured. Some drift in the water column, scavenging what they can find, while others live in sediments, burrowing and waiting for particles to settle. Each species represents a slightly different solution to the same set of problems: how to survive the crushing pressure, the constant cold, the permanent dark, and the scarcity of food. For scientists, studying these crustaceans has revealed just how inventive evolution can be. Consider their aluminum-coated exoskeletons again. Aluminum is not biologically common in surface animals. Most organisms use calcium or silica for structure, but in the trenches, where the pressure is immense and the water chemistry is different, amphipods appear to have found a way to leach aluminum from sediments and incorporate it into their shells. It's not armour in the sense of resisting predators, it's chemistry turned into protection against dissolution, a creative, almost alien-seeming adaptation that could only have arisen in the hadal environment. Even their behaviour is shaped by the demands of the deep. When researchers deploy baited traps into trenches, amphipods are often the first to arrive. Within hours, dozens to hundreds may swarm the bait, tearing into it with powerful mandibles. Their feeding frenzies are fast and efficient, reducing large chunks of meat into scattered bones in astonishingly short times. And then, just as quickly, they disappear again into the darkness, waiting for the next opportunity. Their lives are a cycle of famine punctuated by sudden violent feasts. This role as recyclers makes them critical not just for themselves, but for the entire trench ecosystem. Without crustaceans breaking down organic matter, nutrients would remain locked in carcasses or debris, unavailable to smaller organisms or microbes. With them, energy flows, feeding layers of life that otherwise couldn't exist. In many ways, amphipods and isopods are the foundation of trench communities, not glamorous but indispensable. There's also something strangely comforting about their presence. While snailfish may represent the edges of possibility, pushing the limits of vertebrate survival, crustaceans feel more grounded, more constant. They are everywhere, in almost every trench studied, always present, always busy. Their adaptability makes them reliable. Where there is organic matter, there will be crustaceans. Where there is pressure, cold, and dark, they have already found a way. They don't challenge the boundaries of biology so much as embody its resilience. Humans have even found connections between these creatures and our own activities. Plastics, as mentioned earlier, have been discovered inside amphipods collected from trenches, showing that our pollution reaches even the deepest points on Earth. The fact that these crustaceans eat plastics and incorporate their chemicals into their bodies is both alarming and telling. It shows their indiscriminate survival strategy: eat whatever comes, no matter the source. But it also shows the reach of our influence, a sobering reminder that even the most remote habitats are touched by human hands. Still, the crustaceans endure. They don't complain, they don't resist, they simply adapt. If plastics fall, they eat them. If whale carcasses sink, they consume them. If food is scarce, they wait. Their patience, their flexibility, their capacity to endure extremes makes them emblematic of trench life. They are not fragile, not ghostly like the snailfish, but practical, solid, unyielding in their persistence. Watching footage of amphipods swarming a bait trap can be unsettling. Their pale bodies wriggle and twist, mandibles snapping, a massive motion in an otherwise still environment. It looks chaotic, even savage. But it's simply survival, the raw efficiency of life where nothing is wasted. To us it may seem strange, even alien. To them, it is routine. And perhaps that is the best way to think of crustaceans in the hadal realm. They are not dramatic or rare. They are ordinary in their abundance, yet extraordinary in their ability to exist in a place where life should struggle. They are the workers of the trenches, the scavengers, the recyclers, the constant presence. Without them, the Hadopelagic would be a quieter, poorer, less alive place. With them, it is an ecosystem, sustained not by abundance but by persistence. Most of the time, life in the trenches is governed by scarcity. A few flakes of marine snow drift down each day, a piece of plankton here, a speck of organic debris there. Organisms scrape by, patient and slow, surviving on whatever small particles they can gather. But every so often the deep is shaken by a kind of miracle. A whale dies at the surface, its body sinks through the water column, and eventually it drifts all the way down, landing on the seafloor like a shipwreck made of flesh and bone. When that happens, the rules of scarcity change. A banquet begins. This is the Feast of the Fallen, an event that can sustain life in the Hadopelagic zone for decades. Whale falls are rare, but their impact is immense. A single carcass can weigh dozens of tons, containing more organic matter than might otherwise reach a trench in years. For the organisms waiting below, it is like winning the lottery. Amphipods swarm in first, tearing into the soft tissues, feasting until their bodies bulge with food. Isopods join them, methodical and relentless. Fish arrive too, drawn by the sudden richness. Even the ghostly snailfish, usually unhurried, become predators of opportunity, darting among the swarm to snatch mouthfuls. The seafloor, normally quiet and sparse, transforms into a writhing mass of activity. The process unfolds in stages. At first, the soft tissues are stripped away. Crustaceans and fish work quickly, sometimes reducing a whale's flesh to bones within months. It is a frenzy, a burst of life fed by death. Once the flesh is gone, other organisms move in. Hagfish, polychaete worms and microbes begin to consume the remaining scraps, breaking down fats and connective tissue. Specialized worms known as osedacs, sometimes called zombie worms, bore into the bones themselves, extracting oil and nutrients hidden within. These worms have no mouth, no stomach. They rely on symbiotic bacteria to digest the fats for them, living entirely on the energy locked in whale skeletons. Over time, the whale fall becomes its own ecosystem. Microbes colonize the bones, releasing chemicals that feed other organisms. Sulfides and methane are produced as the fats break down, fueling chemosynthetic bacteria similar to those found at hydrothermal vents. Those bacteria in turn support clams, mussels, and other invertebrates. What began as a whale's death has now become a new community, a city built on decay. For decades, this ecosystem can persist, cycling nutrients through generations of organisms long after the whale's body has disappeared from view. It's astonishing to think about how much life depends on these events. In a world where food is scarce, a whale fall is not just a meal, it's a foundation. Entire lineages of worms, crustaceans and bacteria may owe their survival to the intermittent arrival of these carcasses. Without them, the trenches might be far poorer, far emptier. With them, they are transformed into hubs of activity, temporary but vital. And it isn't only whales. Other large animals, sharks, dolphins, sea turtles, sometimes sink to the depths as well. Even fallen trees carried out to sea can drift down and become food for trench life. But whales, with their immense size and fat-rich bodies, are the most important. They are, in a way, the giants who continue to give long after their lives have ended. Each fall is a reminder of how interconnected the ocean truly is. What happens at the surface eventually shapes what happens in the deepest trenches. From a human perspective, the idea of a whale fall has a strange beauty. Death at the surface becomes life in the deep. One creature's end sustains countless others. It's a cycle we can understand because it mirrors the way ecosystems work on land. Fallen trees feed insects, fungi, and soil microbes. Carcasses sustain scavengers and decomposers, but in the trenches the scale is magnified, the contrast sharper. Here, scarcity is the rule. Here, abundance is shocking. A single whale can turn a desert into a feast. Scientists studying whale falls have found that they pass through 4 distinct stages. First is the mobile scavenger stage, when large animals strip the flesh. Second is the enrichment opportunist stage, when smaller organisms colonize the remaining scraps. Third is the sulfophilic stage, when bacteria thrive on the chemicals released from decomposing bones. Finally, the reef stage, when the skeleton becomes hard substrate for sessile organisms like sponges and corals. Each stage can last years, even decades, turning one fallen whale into a succession of communities. In that sense, the feast is not just a sudden event. It is a slow unfolding, a gradual transformation from flesh to bones to chemicals to reef. The presence of whale falls also raises questions about evolution. Some scientists argue that chemosynthetic communities at vents and seeps may have evolved first around whale carcasses. Before whales, large marine reptiles like plesiosaurs may have played the same role. If true, then whale falls are not just meals. They're evolutionary stepping stones, sites where new forms of life emerged, where partnerships between bacteria and animals were tested and perfected. The trenches may hold not just the remnants of feasts, but the history of how deep-sea ecosystems came to be. Of course, the rarity of whale falls is also part of the story. They don't happen every day. The vastness of the ocean means that many carcasses never reach the trenches, consumed along the way or decomposed before they sink. For organisms waiting below, patience is essential. Amphipods can fast for long periods, living lean until the next bounty arrives. Microbes persist on minimal energy, ready to bloom when new material appears. In the meantime, marine snow continues to fall, sparse but steady, a drizzle of sustenance between storms of abundance. Humans, in our usual way, have managed to intrude even here. In some cases, researchers have deliberately sunk whale carcasses to study the process, creating artificial whale falls to observe how communities form. These experiments have revealed the complexity of the stages, the diversity of species involved, and the sheer efficiency with which the deep sea recycles death into life. They've also shown how fragile the process is. If whale populations decline, fewer carcasses reach the seafloor, and the communities that depend on them may struggle. The health of deep ecosystems is linked directly to the health of surface populations in ways we rarely consider. Watching footage of a whale fall is both eerie and mesmerizing. A massive skeleton sprawled across the mud, ribs arched like the remains of a cathedral, surrounded by swarms of crustaceans and clouds of microbes. It looks alien, as if an ancient shipwreck had become alive again. And yet it is profoundly earthly, the simple continuation of the cycle of life and death. It is strange, and it is ordinary. It is both. For the trenches, these feasts are not just a bonus, they are essential. They break the monotony of scarcity, provide energy for species that would otherwise be unable to persist, and connect the surface world to the depths in a tangible way. They remind us that nothing in the ocean exists in isolation. A whale born in shallow waters, migrating across seas, feeding on krill, eventually dies and becomes the foundation of a community 10 kilometers below. It is a story of continuity, one life feeding countless others, one death sustaining an entire hidden ecosystem. And perhaps that's the most powerful aspect of the Feast of the Fallen. It shows that even in the deepest, most remote parts of the planet, life is not disconnected. The trenches are linked to the surface, not by light or warmth, but by the slow, inevitable sinking of matter. The ocean, vast as it is, remains a single system. Every part affects every other. Even in the silence of the Hadopelagic zone, the fall of a whale proves that connection. When we talk about life in the trenches, it's easy to focus on the creatures we can see, the ghostly snailfish, the giant amphipods, the swarms of crustaceans tearing at a whale fall. But underneath all of that, beneath every scavenger and predator, lies a quieter foundation. Microbes. Tiny, invisible, yet everywhere, shaping the ecosystem in ways more profound than any single fish or crustacean ever could. They are the microbial masters of the Hadopelagic realm, unseen but indispensable, the engineers of survival in a world without sunlight. On the surface, life depends on photosynthesis. Plants and algae capture sunlight, turning it into chemical energy, feeding everything else in the food web. But in the trenches, sunlight never arrives. Photosynthesis is impossible. If life is to persist here, it needs another foundation. That's where microbes come in. They are the ones who take over when the rules of surface life no longer apply. Instead of light, they rely on chemistry. Instead of leaves and chlorophyll, they use enzymes and reactions most of us never learned about in school. They turn the invisible into sustenance, and in doing so, they make the hadal world possible. Chemosynthesis is the key. Some microbes use hydrogen sulfide, others use methane, others still rely on hydrogen or iron. They oxidize these compounds, extracting energy from reactions that to us seem arcane. At whale falls, microbes colonize the bones and fats, breaking them down, releasing sulfides that feed entire communities. At cold seeps, they use hydrocarbons bubbling up from beneath the seafloor, turning them into food. Even in sediments with barely any organic matter, microbes survive, slowly digesting whatever falls from above, particle by particle. They are patient, persistent, and astonishingly adaptable. It's not just about energy. Microbes also recycle nutrients. They break down proteins, fats, and carbohydrates into simpler compounds, which then become available to other organisms. Without them, the trenches would choke on waste, locked up in forms no scavenger could use. With them, the cycle keeps moving. Amphipods can eat flesh, but only microbes can reduce it to its chemical components, ensuring that every atom of carbon, nitrogen, and phosphorus is eventually reused. What's remarkable is their resilience. Deep-sea microbes endure pressures that would crush almost any other cell, yet they thrive. Their membranes are adapted to remain fluid under pressure. Their enzymes are structured to keep working in the cold. Some even rely on piezolites, the same pressure-stabilizing compounds found in fish, though in microbial form the chemistry is even more diverse. Evolution has given them a toolkit broad enough to handle extremes we can barely simulate in laboratories. Scientists have found that many trench microbes can metabolize substances that we might consider pollutants. Plastics, hydrocarbons, heavy metals, all are processed in some form. It doesn't mean pollution is harmless, far from it, but it does mean that microbes are attempting to digest and recycle even the debris we leave behind. Their ability to adapt is astonishing, bending biochemistry into new shapes when faced with challenges evolution never anticipated. And their diversity is staggering. A single scoop of sediment from the Mariana Trench might contain millions of microbial cells, representing thousands of species, most of them unknown to science. Many can't be cultured in laboratories, meaning their functions are inferred from genetic sequencing, and what sequencing has revealed is extraordinary. Entire groups of microbes exist only in the deep sea, lineages that may have been evolving separately for hundreds of millions of years. The trenches aren't just home to strange fish, they're home to strange microbes that represent whole branches of the tree of life we didn't know existed. Their influence goes beyond the trenches. Microbes in deep-sea sediments help regulate Earth's carbon cycle. They lock away carbon for millennia, storing it in forms that stabilize the planet's climate. Others release gases slowly, influencing the chemistry of the ocean and even the atmosphere above. It's humbling to realize that the climate we experience on the surface is partly shaped by invisible organisms living 10 kilometers down. They are not just inhabitants of the trenches, they are global players, their quiet chemical work rippling outward across the planet. What's fascinating is how little energy they need. Some trench microbes survive on what scientists call maintenance metabolism, barely enough to repair their own cells, dividing only rarely, sometimes once in decades. Imagine living on the edge of existence, not growing, not expanding, just persisting. That's what many microbes do in the deep. They embody survival at its most minimalist, proving that life doesn't need abundance to endure. It needs only persistence. At the other extreme, when a whale fall or a seep provides abundant energy, microbial populations explode. They multiply rapidly, coating bones and sediments in mats, glowing under microscopes with fluorescent stains. They shift from patience to abundance instantly, proving they are not just survivors but opportunists, ready to bloom when the moment comes. This flexibility, the ability to endure famine and seize feast, is what makes them true masters. For humans, microbes are easy to overlook. We notice the snailfish because it moves, the amphipods because they swarm. Microbes are invisible, and so we forget them. But the more we study the trenches, the more it becomes clear that without microbes, none of the larger creatures could survive. They are the foundation, the recyclers, the chemists, the unseen workers that make the ecosystem function. Everything else depends on them. There's also the question of origins. Some scientists argue that life may have begun in conditions not unlike those found in the trenches, around hydrothermal vents, where chemistry drives energy instead of sunlight. If that's true, then the microbes of the deep are not just survivors. They are echoes of life's beginning, reminders of how existence first arose on Earth. In their enzymes and pathways, we glimpse not just adaptation but ancient continuity. It's tempting to call them simple, but that would be misleading. Their metabolisms are astonishingly complex, involving reactions we still struggle to understand. Their genetic diversity is vast. Some are symbiotic, living inside the bodies of worms or clams, providing energy in exchange for shelter. Others are free-living, drifting in sediments, independent and resilient. Some even form biofilms that alter the chemistry of rocks, slowly etching patterns into the seafloor. They are not passive, they are active participants in shaping their world, and in the end, that's what makes them masters. Not their size, not their visibility, but their ubiquity and influence. They are everywhere, doing everything, quietly holding the system together. In the trenches, where pressure, cold, and dark should make life impossible, microbes prove it isn't just possible, it's inevitable. When we think about survival in the Hadopelagic, we often marvel at the extremes: fish that glow, crustaceans that grow giant, worms that eat bone. But perhaps the real marvel is that all of it rests on the shoulders of microbes we can't see. They are the silent architects, the foundation stones, the masters of chemistry who make the entire hidden world function. Without them, the trenches would be sterile. With them, they are alive. In the stillness of the trenches, where cold and dark reign almost without interruption, there are places where the earth itself breaks through. Cracks in the seafloor open, water seeps in, and deep beneath the crust it is heated by magma before rising again, bursting back into the ocean in plumes that carry not warmth alone, but chemicals capable of fueling entire ecosystems. These are volcanic vents and seafloor springs, oases of strange energy scattered across the abyss. They are rare, but when they appear, they transform the landscape around them into something alive with possibility. To understand them, imagine water seeping through cracks in the ocean crust. It penetrates deep, meeting hot rock and magma. There, at pressures unimaginable, it heats to hundreds of degrees Celsius. Trapped in those conditions, the water doesn't boil the way it would at the surface, but instead dissolves minerals and metals, carrying them upward. When it finally bursts back out of the crust, it creates hydrothermal vents, chimneys spewing superheated water rich with sulfides, methane, and other compounds. The water, when it meets the near-freezing sea around it, cools rapidly, and the dissolved minerals precipitate, building towering structures that look like smokestacks. Some are black smokers, emitting dark plumes thick with sulfide particles. Others are white smokers, cooler and spewing lighter minerals. Together they dot the seafloor like alien factories, constantly reshaping themselves as minerals build and crumble. Cold seeps are different, gentler but no less important. Instead of superheated water, they release methane, hydrogen sulfide, and other hydrocarbons from sediments, often at the edges of trenches where tectonic activity drives chemical reactions. The seeps don't build towering chimneys, but instead form subtle fields of bubbling water, patches where the chemistry is just different enough to support a hidden community. They're quieter than vents, but their effect on life is profound. What makes both vents and seeps extraordinary is that they provide energy independent of sunlight. At the surface, ecosystems depend on photosynthesis. At these depths, where light cannot reach, the foundation is chemosynthesis. Microbes use the chemicals spewing from vents, or seeping from the seafloor as their energy source, building sugars and organic molecules the way plants use sunlight. Those microbes in turn become food or symbionts for larger organisms. Tube worms, clams, mussels and crabs cluster around vents and seeps, not because the water is warm, but because it is chemically alive. Tube worms are perhaps the most iconic inhabitants of these oases. They can grow meters long, their bodies encased in white chitin tubes, their bright red plumes waving like strange flags in the current. They have no mouths, no stomachs. Instead, they rely entirely on symbiotic bacteria living inside them. The bacteria use sulfides from the vent water to create energy, and the worms provide them with shelter and a steady supply of chemicals. It is a partnership so complete that the worm cannot live without the bacteria. Together they thrive in a place where nothing else of their kind could survive. Clams and mussels have made similar deals. They harbour symbiotic bacteria within their tissues, feeding not on plankton but on chemistry. Crabs and shrimp graze on bacterial mats or hunt smaller organisms that live among the vents. Even fish may be drawn to these places, feeding on the abundance concentrated in patches of seafloor, where the earth itself provides the fuel. For a few square meters, the rules of scarcity in the trenches are suspended. Life blooms in strange concentrated forms. And yet, these communities are fragile. Vents don't last forever. The chimneys grow, collapse and shift. The heat source may move, cutting off the flow of chemicals. When that happens, the community disappears. Organisms dependent on the vent die or drift away. The oases vanish, leaving behind mineral towers that become lifeless ruins. Cold seeps last longer, but even they are temporary on geological timescales. The chemical trickles eventually stop, and the creatures that depended on them fade away. For all their richness, these places are reminders of impermanence. Still, while they last, they are remarkable. Scientists have suggested that life on Earth may have begun in conditions much like these. Hydrothermal vents provide gradients between hot and cold, acidic and alkaline, chemical-rich and chemical-poor, that could have driven the first primitive metabolisms billions of years ago. In that sense, every vent is not just an oasis, but a glimpse into the origin of life itself. Studying them isn't only about understanding today's ecosystems, it's about peering back into the planet's earliest history. The connection to the trenches is especially important. While not all hydrothermal vents are found at hadal depths, many trenches host seeps and vent-like features. The shifting plates and immense pressures create cracks where fluids escape. Microbes colonize them. Larger animals follow. In the midst of darkness and cold, these sites provide stability, sometimes even abundance. For scientists lowering landers into trenches, stumbling upon a seep field is like finding a hidden garden. Where the rest of the seafloor is sparse, suddenly there are dense clusters of clams, worms and crustaceans. For the animals, these sites are more than food. They are anchors in a drifting world. In the vast emptiness of the hadal plains, a vent or seep provides a fixed point, a place to settle. Organisms that might otherwise wander or scatter can congregate. Communities form. Interactions multiply. Predators and prey find each other in ways impossible in the open mud. These patches become laboratories of adaptation, places where evolution tests new strategies. Humans too are drawn to them. Hydrothermal vents were first discovered in 1977, and since then they have fascinated scientists and the public alike. The idea of life thriving without sunlight, relying instead on Earth's heat and chemistry, was revolutionary. Cold seeps, discovered later, added another layer to the picture, showing that even without heat, chemistry alone could sustain ecosystems. These discoveries expanded our imagination, not just for Earth, but for other worlds. Moons like Europa and Enceladus, with their subsurface oceans, might host life around similar vents. Studying the hadal seeps and vents is, in a sense, practice for understanding the possibilities of life beyond Earth. Yet as with so much in the deep sea, our presence carries risks. Deep-sea mining threatens vent fields, targeting the mineral-rich chimneys for extraction. Cold seep communities may be disrupted by drilling or trawling. Because these ecosystems are so rare, their loss would be profound. Each vent field is unique, hosting species found nowhere else. Destroy one, and you erase a community millions of years in the making. Still, they endure for now, scattered across the ocean floor like secret cities. They remind us that life does not need sunlight, that the rules we thought were universal are not. Plants and photosynthesis may dominate the surface, but in the trenches, microbes and chemistry are the foundation. Tube worms, clams and crustaceans live not because of the sky, but because of the earth beneath. It is a reversal of perspective, a reminder that life is adaptable far beyond what we expect. So as we drift through the trenches, picturing amphipods scavenging, snailfish hunting, microbes recycling, we can now add vents and seeps to the image. They are the glowing hearths in an endless dark, not with fire but with chemistry. Quiet plumes and trickles that turn rock and water into food. They are rare, they are fragile, but they are also proof of life's inventiveness, small gardens in the deepest abyss. When people imagine the trenches, they often picture absolute silence, a place so deep, so cut off, that nothing could break the stillness. And in a way, that impression makes sense. There is no wind down here, no waves crashing, no rain falling, no surf pounding the shore. The Hadopelagic zone is far removed from the surface drama of the ocean. But silence is never quite true. The deep is not empty of sound. It is full of mysteries carried on vibrations, noises faint and strange, echoes that behave differently under the weight of all that water. If light is absent here, sound becomes one of the only ways information moves. Water carries sound better than air. It's denser, and that density allows sound waves to travel farther and faster. In the trenches, where the pressure is immense and the water is consistently cold, sound can travel incredible distances. A low-frequency noise made thousands of kilometers away can eventually reach the depths, faint but still distinct. The deep is not silent, but instead connected by an invisible web of sound that drifts in from far away. For the creatures living here, that fact is crucial. Light cannot reach them, but sound can. It becomes one of the only cues about what is happening in their environment. Some fish may detect vibrations from prey or predators. Crustaceans might sense subtle shifts in the water, tiny clicks or pulses that betray movement. Even microbes can be influenced by vibrations in ways we don't fully understand. Sound, or at least vibration, is part of life at every level, even if it is not as obvious as in the world above. The Hadopelagic zone also acts as a strange amplifier of sound. At certain depths, conditions create what scientists call a sound channel, where sound waves are trapped and can travel with little loss for thousands of kilometers. It means that noises from distant storms, from whale songs, even from human ships or machinery, can end up resonating in the trenches. For the organisms that live there, the soundscape is not silent. It is a constant background of distant rumbles, clicks and pulses. Some of those sounds are biological. Whales, especially, produce calls that can travel enormous distances. Their low mournful songs echo through the ocean and sometimes reach deep into trenches. For a snailfish or amphipod, those noises may be faint, perhaps imperceptible, but they are there. Other sounds come from smaller creatures. Snapping shrimp that produce sudden cracks, fish that grind or drum their muscles to signal to each other, even the scraping of crustaceans feeding. Put a sensitive hydrophone in the deep, and the water is alive with noise. And then there are the geological sounds. The earth itself speaks into the trenches. Submarine earthquakes rumble through, sometimes powerful enough to shift sediments. Volcanic eruptions release booming roars as gases burst into the water. Even slow processes like the grinding of tectonic plates create groaning, creaking noises that carry into the depths. These sounds are reminders that the Hadopelagic zone is not just biological, but geological, shaped by forces deep within the planet. Humans too have added their voices. Ships produce constant low-frequency hums. Sonar pings echo downward. Seismic surveys create powerful blasts that penetrate the seafloor. These sounds travel far, often farther than their makers intended. In recent decades, hydrophones in trenches have recorded an increase in human noise, a sign that even the most remote parts of the ocean are not untouched. For the organisms that rely on subtle sound cues, that intrusion may be disruptive, though we're only beginning to understand how. One of the most mysterious sounds ever recorded from the deep was nicknamed the bloop. Detected in 1997 by hydrophones thousands of kilometers apart, it was an ultra-low frequency sound that seemed to originate somewhere near the South Pacific. For years, it fueled speculation. Was it a giant squid? A massive unknown creature lurking in the depths? Eventually, scientists concluded it was most likely the sound of icebergs cracking and breaking apart. But the fascination it sparked shows how easily we imagine sound as a clue to hidden life in the deep. The trenches, being so poorly explored, remain fertile ground for such mysteries. Other strange sounds have been recorded as well. Moans, pings, and unclassified noises that don't match known geological or biological sources. Some have been explained later, others remain puzzling. For scientists, each unexplained sound is a reminder that the hadal world is still largely unknown. The creatures of the deep might communicate in ways we have yet to recognize, their whispers masked as background noise. Or perhaps the planet itself is speaking in tones we don't fully understand. For the animals that live here, what matters most is not our interpretation but their own. Imagine being a snailfish, surrounded by blackness, relying on faint shifts in water pressure to detect an amphipod nearby. Imagine being a shrimp clicking its claws to signal others, the vibrations carrying farther than light ever could. Imagine being a worm nestled in a vent community, the steady rumble of geothermal activity forming the background of your world. For them, sound is not mysterious. It is ordinary. It is their way of knowing. And yet, the silence is real too. Not the absolute silence of nothingness, but a silence compared to our noisy surface world. In the trenches, sounds are rare, punctuating long stretches of stillness. A faint groan of the earth, a distant whale call, a sudden click of shrimp, then quiet again. It is a soundscape defined by contrast, by long waiting and brief interruptions. To human ears it feels haunting. To hadal creatures it is simply home. Scientists studying the soundscape of the deep often describe it as layered. The lowest frequencies are the background hum of the earth and distant storms. Above that come the moans and calls of whales. Then sharper the clicks of smaller animals. At the top, almost inaudible, are the faint scrapes and shifts of microscopic life. Together, they create a spectrum that is more complex than we first assumed. Far from silent, the trenches are filled with overlapping voices. This has important consequences for survival. Predators may use sound to detect prey. Prey may use it to avoid predators. Some animals might even communicate with sound, though in ways subtle enough to escape our instruments. Hydrophones have picked up patterns that suggest rhythms, repeated pulses that could be communication. Whether those belong to known creatures or something we haven't discovered yet is still uncertain. In the deep, every answer seems to lead to more questions. It also changes how we think about exploration. Cameras show us what the trenches look like, but hydrophones reveal what they sound like. Both are necessary to understand the environment fully. Listening to the deep is, in many ways, easier than seeing it. Sound travels farther, covering distances that light and vision cannot. Hydrophones can sit quietly for months or years, recording everything, while cameras can only show what passes in front of them. The future of hadal exploration may depend as much on listening as on seeing. What's certain is that silence is an illusion. The trenches are not mute. They are filled with whispers, groans, cracks and songs. To us, those noises may seem faint, incomprehensible, or mysterious. To the creatures living there, they are as natural as sunlight is to us. They are the cues, the rhythms, the signals by which life endures in the dark. For most of history, the trenches were places of imagination more than knowledge. Sailors and storytellers spoke of monsters lurking below, unseen giants waiting in the dark. The truth, as we've come to learn, is stranger and subtler, but to reach that truth required something rare. The courage and technology to go down there ourselves. Strange encounters don't happen by accident in the Hadopelagic zone. They happen when humans build machines strong enough to withstand pressure that would crush steel, when explorers risk descent into the black, when cameras and landers are lowered into the unknown. Each expedition has been a step into mystery, and each has revealed life we didn't know was possible. The first attempts to probe the deep were indirect. Weighted lines were dropped into the ocean to measure depth. Nets were hauled up, often broken or empty. Samples gave hints, but never the whole picture. For a long time, scientists argued whether life could exist at extreme depths at all. It wasn't until the 20th century, with the invention of deep-diving submersibles, that we began to learn the truth. The bathyscaphe Trieste, in 1960, was the first to carry humans into the Mariana Trench. Jacques Picard and Don Walsh descended nearly 11 kilometres, sitting inside a tiny steel sphere, peering through a single window into the abyss. At the bottom they reported seeing a flatfish-like creature, though whether it was truly a vertebrate or some invertebrate is still debated. What mattered more was the fact that something was alive down there. The trenches were not sterile. They were inhabited. That dive became legendary, not because it told us everything, but because it proved that exploration was possible. The Trieste was a crude machine by modern standards, but it opened a door. Later expeditions followed, using remotely operated vehicles, autonomous landers and more advanced submersibles. Each one carried lights, cameras and instruments, allowing us to see what our own eyes never could. The images they sent back were haunting. Amphipods swarming bait, snailfish drifting like ghosts, vents spewing mineral-rich plumes. The hadal world was no longer myth. It was real, visible and endlessly strange. And yet, for all our technology, every encounter still feels uncanny. Machines lowered into the trenches capture footage of creatures that look like they belong in science fiction. Translucent fish with soft, gelatinous bodies, crustaceans glowing faintly, worms boring into bones. Sometimes the footage shows things we can't identify at all, flickers of movement that vanish before the camera can focus. Each descent is a reminder that we've only scratched the surface. There are stories that come back from these expeditions that sound almost unbelievable. In some trenches, landers have recorded amphipods stripping bait fish down to skeletons in minutes, their frenzy so intense that it looks like the bait is dissolving. In others, cameras have captured snailfish thriving at depths thought impossible, calmly gliding past the equipment as if to remind us that our rules don't apply down here. And occasionally microphones have picked up mysterious sounds, moans, pings and rumbles that suggest something larger moving nearby. We don't always know what they are. Human explorers have been equally captivated. James Cameron's solo dive into the Mariana Trench in 2012 was one of the most publicised expeditions of recent decades. Sealed inside a green submersible designed for the task, he descended to nearly 11 kilometres, spending hours on the seafloor filming and collecting samples. What he described afterward was both desolate and full of potential, a world of alien landscapes, sharp ridges and unexpected life. His mission proved that even in the modern age exploration is still possible, still dangerous, still thrilling. But perhaps the strangest encounters are not always dramatic. Sometimes they are subtle. A tiny amphipod with plastic fibres inside its stomach, proof that human activity has reached the deepest points on Earth. A microbial mat glowing faintly under ultraviolet light, hinting at chemistry we don't fully understand, a sudden, inexplicable pulse of sound that echoes through the hydrophones, leaving scientists puzzled for years. In the trenches, even the smallest detail can feel extraordinary, because it breaks through the silence and scarcity with a reminder that life is still active, still adapting. Every expedition is also a test of our own limits. Machines sent into the deep must be engineered to survive pressures 1,000 times greater than at the surface. Cameras must operate in total darkness. Arms must be delicate enough to collect samples, but strong enough not to break under strain. Each success is an engineering triumph, each failure a reminder of how inhospitable the trenches are to human presence. More than once, equipment has been lost, crushed, or simply vanished into the dark, never to return. Strange encounters aren't always with creatures. Sometimes they're with the environment itself, a reminder that the planet resists our intrusion. And yet, the pull of curiosity is too strong. We keep going back. Each expedition brings new species, new data, new glimpses of a world that refuses to be fully known. Scientists sometimes joke that every trench dive is guaranteed to find something new because the territory is still so unexplored. That's not really a joke, it's reality. Every time a camera descends, we add to our catalogue of the unknown. Strange jellyfish-like organisms, delicate worms with feathery appendages, crustaceans armoured in unexpected ways. Even the sediment yields surprises, microbes that metabolize in ways we never imagined, genes that hint at entirely new branches of the tree of life. The encounters also carry an emotional weight. For the explorers watching footage from thousands of meters below, there is awe but also humility. To see life thriving in places we once thought impossible is to be reminded of how little we know. For some, it sparks comparisons to space exploration. The deep ocean feels as alien as another planet, and in many ways hard to reach. The irony is that we've sent more people to space than to the deepest trenches. Strange encounters with trench life are rarer than encounters with the moon. For the creatures themselves, of course, there is nothing strange about it. The amphipods swarming a bait trap are simply feeding. The snailfish gliding past a submersible is just continuing its daily life. The microbes colonizing a vent are doing what they've done for millions of years. It's only strange to us because we are intruders here, seeing what was never meant for our eyes. To the hadal world, we are the oddity, the brief interruption in an otherwise endless cycle of survival. And maybe that is the greatest lesson of these expeditions. We go looking for monsters, for impossibilities, for shocking revelations. What we find instead is life, ordinary in its own context, extraordinary only to us. Strange encounters, yes, but only because they reveal how narrow our sense of normal really is. In the deep, soft-bodied fish, swarming crustaceans and silent microbes are not strange. They are home. Every time a human descends into the trenches, it feels like a triumph. News outlets call it historic. Explorers describe the surreal beauty of the seafloor. Engineers celebrate the technology that made it possible. And all of that is true. But underneath the triumph, there is a quiet truth we rarely acknowledge. Our presence in the Hadopelagic zone is always temporary, always fragile, always balanced on the edge of impossibility. The limits of human presence here are sharp, absolute, and humbling. Think first of the pressure. At 10 or 11 kilometers down, the water above weighs so heavily that every square inch of a submersible hull is pressed with more than 1,000 times the atmospheric pressure we feel at sea level. For a human body, that pressure is instantly fatal. Lungs would collapse, blood would boil, bones would shatter. There is no adaptation possible for us. We are creatures of the surface, built for one atmosphere, and without protection we cannot survive even a few meters beneath the waves for long. In the trenches, the difference is not slight. It is categorical. That is why every expedition relies on technology. The steel sphere of the Trieste, the composite hull of James Cameron's deep-sea Challenger, the titanium and syntactic foam of modern submersibles. These are not luxuries, but lifelines. They are the only things standing between explorers and instant destruction. The walls of these vessels are measured in centimetres of metal and resin, yet they hold back a force that could crumple ships. Every bolt, every weld, every panel is a test of engineering, and even when they succeed, the explorers inside are sealed away, unable to touch or feel the environment around them, only able to observe through glass or cameras. Human presence is mediated, distant, buffered by machines. The limits extend beyond pressure. The cold is unrelenting, just above freezing, sucking heat from anything unprotected. Electronics and batteries must be carefully insulated. Human bodies would lose warmth too quickly, even with protective suits. But since no one can survive exposed anyway, we remain cocooned inside vessels heated artificially. Then there is the darkness. Without lights carried down with us, nothing can be seen. Vision in the trenches is always artificial, a narrow cone of illumination that captures only what falls directly within it. To be there is to know you are surrounded by life and terrain that remain unseen, because our presence can never expand far enough to take it all in. Duration is another hard boundary. Submersibles carry only so much oxygen, only so much power. Hours, not days, are the measure of our stay. Even unmanned landers and remotely operated vehicles face similar limits. Power runs low, cables snap, mechanical arms break. The trenches are not a place where humans can linger. They are a place we borrow, briefly, before retreating. Every encounter, no matter how profound, is measured against the ticking clock of return. The cost is also a limit. Each expedition requires years of planning, millions of dollars, teams of engineers, and fleets of support ships. To visit the Hadal zone is not like climbing a mountain or even launching into orbit. It is rarer, more complex, more fragile. Only a handful of dives have ever reached full trench depths. The number of people who have seen the bottom of the Mariana with their own eyes could fit around a dinner table. That exclusivity is not because the trenches are uninteresting, but because they are so difficult. For every dive completed, countless attempts are never made at all, blocked by logistics, budgets, or the sheer difficulty of engineering. And then there is biology. Specimens collected from the trenches rarely survive the trip to the surface. The same pressures that make it impossible for us to live down there also make it impossible for many hadal creatures to live up here. Their bodies rupture, their proteins denature, their forms collapse. What we encounter alive in their world rarely survives entry into ours. Human presence, in that sense, alters what it observes. We see the trenches only through filters, through cameras that work in the dark, through submersibles that withstand pressure, through samples that change on their way up. We are never seeing the world as it truly is. We are always seeing a version bent to meet our limits. There's a paradox in this. The Hadopelagic zone is the largest habitat on Earth, yet it is the least visited. It covers vast stretches of the seafloor, deeper than mountains are tall, but our presence there has been measured in hours. We send spacecraft across the solar system, with more ease than we send people into the trenches. The irony is that the world we live on remains less explored than the ones we imagine beyond it. Our limits in the deep remind us that we are, at heart, surface creatures with only temporary visas to the abyss. Still, we try to stretch those limits. Engineers design better materials, vessels that can withstand pressure with more safety, landers that can stay longer, sensors that can listen without interruption. But no matter how far we advance, there will always be constraints. We cannot live there. We cannot build cities on the trench floor. We cannot make it our own. Human presence in the Hadopelagic will always be transient, always borrowed. And perhaps that is fitting. The deep does not belong to us. It belongs to the organisms that have adapted to it for millions of years. The snailfish, the amphipods, the microbes. They are at home where we are not. Our presence is strange, brief, disruptive. Their presence is ordinary, constant, enduring. The limit is not just technological. It is existential. We are not of this place. That doesn't make the effort meaningless. On the contrary, every dive, every sample, every moment of footage is invaluable. They remind us that life thrives in conditions we once thought impossible, and they expand our sense of what biology can do. They show us that Earth is more varied, more resilient, more astonishing than we imagined. But they also remind us of humility. For all our power, all our inventions, all our ambitions, there are places we can only visit, never inhabit. So the next time you see an image from the bottom of the Mariana, a pale snailfish gliding across the seafloor, or a swarm of amphipods tearing at bait, remember what it represents. Behind that image lies a machine built to withstand impossible pressure, a team of people pushing against the limits of what humans can do, and a reminder that those limits still hold firm. The trenches are not ours, they never will be, and that may be the most important lesson of all. When people talk about the unknown, the first image that comes to mind is often the stars. Space has always been our metaphor for mystery, the endless void that stretches beyond the horizon of sight. We build telescopes to study it, rockets to reach it, fantasies to fill it. But the truth is that an equally vast and alien world lies beneath our feet, hidden under the ocean. The Hadopelagic zone, in its silence and darkness, mirrors the cosmos in ways that are striking once you notice them. To peer into the trenches is, in many respects, to look into space without leaving Earth. The first similarity is obvious. Both are places where humans do not belong. Space offers a vacuum, deadly radiation, and temperatures near absolute zero. The trenches offer crushing pressure, constant cold, and total darkness. In both cases, survival requires machines, protective shells, and a careful rationing of time. Astronauts in orbit float in fragile stations dependent on life support. Explorers in submersibles descend into fragile spheres, dependent on oxygen tanks and hulls. In neither place can we breathe freely, walk freely, or linger indefinitely. Presence is always borrowed, always temporary, always at the edge of disaster. Both environments also resist exploration. Reaching orbit or the moon requires immense engineering, but so does reaching the trench floor. In fact, more people have walked on the lunar surface than have visited the Challenger Deep. We treat the cosmos as the great frontier, yet the deep ocean remains more unvisited, more mysterious. Maps of Mars are more detailed than maps of Earth's seafloor. In that sense, the hadal depths are our own inner space, the uncharted frontier hiding within the planet itself. The parallels extend beyond difficulty. The creatures of the trenches resemble what we imagine alien life might look like. Transparent, soft-bodied fish that yield to pressure instead of resisting it. Crustaceans coated in aluminum, feeding on scraps in the dark. Worms that live inside bones, bacteria that thrive on sulfides and methane. These are not the plants and mammals of the surface. They are organisms built for a world entirely different from ours, shaped by rules that feel unfamiliar. When astrobiologists speculate about life on Europa or Enceladus, moons with oceans sealed under ice, they often point to the deep sea as the best model. If life exists elsewhere in the solar system, it may look less like us and more like a snailfish, an amphipod, or a mat of chemosynthetic microbes. Then there is the question of energy. On the surface, and in our daily lives, sunlight is the foundation of everything. Plants use it to grow, animals eat plants, and the chain continues. In space, sunlight is also what we imagine sustains planets and moons. But in the deep, as at potential alien oceans, sunlight is irrelevant. Life feeds on chemistry instead, turning sulfides and methane into energy, building entire ecosystems without ever seeing a ray of light. If life exists elsewhere, far from a star's warmth, it might use the same trick. In that way, the trenches are not just mirrors of space, they are laboratories for it. The scale of both also inspires awe. Look up at the night sky, and the immensity is overwhelming. Look down into a trench, and the immensity is no less real. The Mariana Trench is deeper than Mount Everest is tall. The pressure at the bottom is beyond what we can easily imagine. Just as space dwarfs us with its distances, the Hadopelagic dwarfs us with its depth. In both, we're reminded of our smallness, our fragility, our place as creatures of a thin surface layer clinging to a planet we can't fully comprehend. Even the way we explore them is similar. We send probes first, machines that can endure what we cannot. Rovers crawl across Mars, telescopes scan the stars, hydrophones and remotely operated vehicles descend into trenches. Later, if possible, we send people, but only for brief visits. The majority of our knowledge comes not from direct human presence, but from instruments that extend our senses into places we cannot go ourselves. Whether in orbit or in the Hadopelagic, we rely on cameras, sensors and data streams. We're explorers by proxy, dependent on machines to translate the unknown into something we can understand. There is also the allure of mystery. Every photograph of a distant galaxy, every grainy image of a trench-dwelling creature stirs the same feeling. What else is out there? What haven't we seen yet? Both space and the deep ocean are vast enough that most of them remain hidden. Every expedition finds something new because there is so much left to discover. That sense of endless possibility keeps us returning, despite the risks, despite the costs. It keeps our imaginations alive, filling the gaps with speculation until we have evidence. And just as with space, the deep raises philosophical questions. If life can thrive in the trenches, in darkness, in crushing pressure, then what does that say about the limits of life elsewhere? If microbes can metabolize methane under kilometers of water, why not on another planet? If snailfish can survive where no vertebrate should, why not something similar beneath the icy crust of Europa? The deep becomes not just a mirror of space, but a key to understanding it. Studying one helps us imagine the other. Yet for all the similarities, there is a difference that makes the comparison even more striking. Space is far away. The trenches are here. You could stand on a beach and point toward a trench just a few hundred kilometers offshore, and yet it remains as inaccessible to you as the moon. That proximity makes the mystery sharper. The unknown is not only out there in the stars, it is under our own seas, surrounding us, hiding just beneath the waves. In that sense, the deep is not just a mirror of space. It is a reminder that the alien is already part of our own world. Every time explorers return from the trenches, they describe the same feelings astronauts have in space. Awe at the scale, humility at their fragility, wonder at the beauty of what they saw, and always a sense of how much remains unknown. The Hadopelagic zone reflects the cosmos, not because it looks the same, but because it evokes the same response in us. It is a frontier that reminds us how small we are, how resilient life is, and how much mystery still surrounds us. When scientists describe the trenches, the language often turns from data to wonder. Numbers can explain the pressure, chemistry can explain the adaptations, but none of that captures the feeling of knowing a place like the Hadopelagic zone exists beneath us. It's not only a scientific frontier, it's also a philosophical one. To look into the abyss is to be reminded of questions we rarely ask on the surface. Questions about survival, about limits, about meaning in a universe where most of it is hidden from us. The abyss forces us to think differently, because it shows us a version of life stripped down to its essentials. At first glance, the trenches might seem inhospitable, a reminder of how fragile life is. Darkness without end, pressure that crushes steel, cold that never warms, food so scarce it can take months for a creature to find a meal. By our standards, these are conditions meant to exclude life. And yet, the hadal zone is not empty. It is alive, full of organisms that not only endure but flourish. Their existence raises a simple but profound truth. Life does not need our conditions to thrive. It doesn't need light. It doesn't need warmth. It doesn't need abundance. It needs only adaptability. That fact alone reshapes how we think about our place in the universe. There is humility in that realization. We tend to believe that the way we live, the way life exists at the surface, is the measure of what is possible. The abyss shows us otherwise. Our environment is one version among many. Our needs, for air, for light, for warmth, are not universal. They are just local adaptations. The snailfish's need for piezolites, the amphipod's ability to gorge and wait, the microbe's capacity to metabolize methane. Those are equally valid, equally ordinary in their own context. To them, we are the fragile ones, dependent on a narrow range of conditions, unable to survive without them. The abyss reveals that fragility by showing us other ways life can be. It also forces us to think about time differently. On the surface, life moves quickly. Seasons change, plants grow, animals migrate. In the deep, the pace slows. Food is rare, so organisms wait. Energy is precious, so metabolisms crawl. Some microbes may divide only once in decades. Some scavengers may gorge once and then fast for months. Life here is measured not in days or seasons, but in years and centuries. Patience is not just a virtue, it is survival. And in that patience there is a lesson for us, that endurance is often more powerful than urgency, that persistence matters as much as action. The abyss also asks us to reconsider abundance. On land, and even in shallow seas, we're used to environments overflowing with life, green forests, coral reefs, flocks of birds. In the trenches, abundance is rare, but when it comes, in the form of a whale fall or a vent community, it is transformative. Whole ecosystems bloom around a single source. From scarcity, abundance grows, and when it ends, life retreats again into patience. There is something philosophical in that rhythm. It tells us that meaning is not in constant plenty, but in cycles, in the rise and fall, in the way life adjusts to what is given. There's also the matter of perception. We see the abyss as alien, frightening, strange, but for the creatures that live there, it is ordinary. They are not struggling or suffering, they are simply alive, doing what they were made to do. To call the abyss hostile is to project our own limitations onto it. To a snailfish, it is not hostile, it is home. That shift in perspective is important. It reminds us that the universe is not shaped for us. It exists as it is, and life finds ways to fit into it. The abyss, in that sense, is a mirror for our own assumptions. It shows us how narrow they are. Human presence in the trenches is fleeting, as we've seen. But perhaps that is also part of the philosophy they offer us. We are not meant to stay everywhere. Not every place is ours to inhabit. Some are only for visiting, for learning, for respecting from afar. The abyss reminds us that exploration does not mean ownership. It means humility, curiosity, and the willingness to accept that some mysteries remain beyond us. The trenches also spark questions about resilience. How much can life endure? What forms can it take? The hadal organisms show us that survival is not about resisting change but embracing it. Soft bodies yield to pressure. Flexible metabolisms yield to scarcity. Glow replaces sunlight. Every adaptation is an act of acceptance. There's a quiet philosophy in that. Survival is not defiance, it is harmony. Life doesn't argue with the abyss, it becomes part of it. And then there is the symbolic weight of the abyss itself. For centuries, humans have used it as a metaphor for fear, for the unknown, for death. Staring into the abyss is a phrase heavy with dread. But when we actually look at the hadal abyss, what we see is not emptiness. We see life, persistence, subtle beauty. The abyss is not death. It is another form of existence. To stare into it is not to confront nothingness, but to confront difference. That realization softens the metaphor, replacing fear with wonder. Of course, philosophy also means grappling with limits. The trenches show us both the possibilities of life and the boundaries of our own. We cannot survive there. We cannot live without machines. We cannot fully see or hear what happens in those depths. But instead of despair, that limitation can inspire awe. It reminds us that we are not the measure of all things. We are part of a larger system, one in which other creatures thrive where we cannot. That perspective is humbling and perhaps necessary in a world where we so often assume control. The abyss also raises ethical questions. If life here is so rare, so slow, so dependent on fragile cycles, what responsibility do we have to protect it? Mining, drilling, and pollution reach even the trenches. Amphipods with plastic fibres in their stomachs are proof. If we disrupt whale populations at the surface, we reduce the feasts that sustain the hadal communities. Our choices ripple downward. To recognise that is to accept that philosophy is not only about ideas, it is about action. The abyss challenges us to extend our sense of responsibility to places we will never live, to creatures we will never see. Finally, the trenches force us to think about mystery itself. We often believe that knowledge is within our grasp, that science will eventually explain everything, but the abyss resists. For every snailfish we film, there are countless creatures we haven't. For every sample we bring up, there are billions of microbes we'll never culture. For every sound we identify, there are others we cannot. The abyss remains unknowable in full, and that unknowability is part of its meaning. It reminds us that mystery is not a gap to be filled, but a reality to be respected. So what is the philosophy of the abyss? It is patience in scarcity. It is resilience in extremes. It is humility in the face of limits. It is recognition that life takes forms we would never imagine, and that our way of existing is only one among many. It is a mirror for our assumptions, showing us how fragile and how narrow they are. It is a call to responsibility, reminding us that even the deepest places are touched by our actions. And it is an invitation to wonder, to accept that mystery is not weakness but strength. The trenches are not just a scientific frontier, they are a philosophical one. They teach us about ourselves by showing us what we are not. They remind us that survival does not mean control, that life is larger than our imagination, that existence itself is richer than our narrow window on it. To look into the abyss is not to see emptiness, it is to see possibility. And in that possibility lies a lesson that no other place on Earth can teach so clearly. Thank you for staying with me all this way. We've drifted together through darkness, followed faint glimmers of light, listened to whispers carried in pressure and silence, and walked step by step across landscapes no human feet will ever touch. The Hadopelagic zone is not a place we can call home, and yet in learning about it, we've come to recognise it as part of our own story. This is the closing, but not an ending, because the deep is not finished speaking to us. It still has things to tell, if only we learn to listen carefully. We began at the surface, where the ocean feels familiar, where sunlight turns waves silver and the air tastes of salt. From there, we descended, deeper and deeper, leaving behind colours, warmth and sound. Each kilometre down stripped away something we took for granted until we arrived in a world where only survival and adaptation remain. Yet what we found was not emptiness. We found life. Delicate, strange, inventive life, holding on in ways we never expected. That journey itself is a whisper from the deep, telling us that life is not fragile in the way we thought. It is resilient, creative, endlessly adaptable. And through all of it, the hadal zone has been showing us lessons without ever speaking in words. The snailfish gliding past a camera shows us patience and fragility coexisting with strength. The amphipods swarming a whaleful show us the importance of cycles, of abundance born from death. The microbes clinging to vents remind us that even the smallest actors can support entire worlds. Together they form a chorus of quiet truths, carried upward through science, through philosophy, through imagination. What makes the abyss compelling is not just the creatures or the geology, it's the way it reflects ourselves back to us. To see life thriving in a place we thought impossible is to see possibility beyond our assumptions. To feel the limits of our own presence, there is to remember humility. To hear echoes of distant wails or tectonic rumbles is to be reminded that silence is never empty. The whisper of the deep is layered. It speaks of survival, of mystery, of connection, and of endurance. Think for a moment of how connected it all is. A whale dying at the surface eventually sustains amphipods 10 kilometers down. Microbes in trench sediments help regulate the carbon cycle that shapes our climate. Human actions, plastics, sound, overfishing, ripple into the abyss, changing lives we will never see. The hadal zone may seem distant, cut off, hidden, but in truth it is tied to us, as much a part of the Earth system as a forest or a sky. To forget it would be to forget part of ourselves. The whisper is also about mystery itself. We like to imagine that one day science will explain everything, that there will be no more secrets left. But the abyss resists that dream. No matter how many expeditions we send, there will always be more life unseen, more sounds unexplained, more adaptations waiting in the dark. The whisper tells us that mystery is not a failure to be solved, but a condition of the universe. The unknown is not something we erase. It is something we live with, something that keeps curiosity alive. And maybe that's why the deep feels so moving, not because it is frightening, though it can be, not because it is strange, though it certainly is, but because it shows us that the universe is wider than our imagination and that life has ways of existing we never considered. The whisper tells us that survival is not about domination, but about harmony. It tells us that endurance is not about abundance, but about patience. It tells us that meaning is not found only in the light, but also in the dark. For centuries, people have used the word abyss as a metaphor for fear. To stare into it was to stare into death, into nothingness, into despair. But when we actually look into the real abyss of Earth, we find something different. Not emptiness, but life. Not despair, but resilience. The whisper from the deep changes the metaphor. It replaces dread with wonder. It shows us that the abyss is not something to fear. It is something to respect, to learn from, to be humbled by. So as we close, think of where you are right now. Perhaps you're listening in a quiet room, perhaps late at night, perhaps on a morning commute. Wherever you are, know that beneath the surface of the ocean, far deeper than you can see, life is still going on. Snailfish are still drifting, amphipods are still scavenging, microbes are still turning chemistry into sustenance. The abyss is still alive, whispering its truths into the world above. Our presence here may be brief, but the lessons last. And if you found this journey soothing, if you felt the pull of curiosity and calm together, remember to stay connected with us. This channel, Life Beyond Seen, is built to share stories like these. Stories that show us what lies hidden, what lies forgotten, what lies beyond the ordinary. If you want to keep wandering through these unseen worlds, you can like, subscribe, or simply return next time. Every story adds another thread to the larger picture of life, and your presence here helps weave it together. The whisper from the deep is gentle, but it is persistent. It tells us that survival can take forms we never imagined. It tells us that humility is not weakness, but wisdom. It tells us that the unknown is not empty, but full of potential. And it tells us quietly but firmly that our world is more alive, more interconnected and more astonishing than we ever thought. So let the whisper stay with you as you step away from this story. Carry it with you into the surface light, into the rhythms of your own life. Let it remind you that mystery is not far away. It is beneath your feet, in the deep ocean, in the places you will never see. And let it remind you that life in all its strange and patient forms endures, always.